Maltesers, Twix and Bounty look simple until you see what happens behind the scenes. One is built around a crisp malted center, one is layered with caramel, and one hides a soft coconut core beneath smooth chocolate. Today, we step inside the factories behind these iconic candies and uncover how each one is shaped and finished before it reaches the shelf. Maltesers begin with a brittle malt center expanding into a tiny honeycomb sphere. The center is the part that makes the product different from an ordinary chocolate ball. It is light, crisp, and porous, with a dry snap inside a smooth milk chocolate shell. The manufacturing line is designed to build that contrast in stages. First the malted center, then the rounded shape, then the chocolate layers, then polishing, cooling, weighing, bagging, and final packing. The malt center starts as a cooked mixture. Malt extract, sugar, glucose syrup, milk ingredients, and other dry components are measured into a controlled batching system. The ingredients enter mixing vessels, where heat and agitation turn them into a thick syrup. The syrup must be uniform before it can be aerated and expanded. Malt extract gives the center its toasted, cereal-like flavor. It blends into the sugar system as the liquid warms. The mixture becomes darker, thicker, and more elastic. Agitators keep it moving so the sugars do not settle or burn against heated surfaces. The syrup then moves into a cooking stage. Heat drives off moisture and concentrates the sugars. The liquid becomes more viscous as water evaporates. Its temperature and solids level must reach the correct point, because the final texture depends on how the sugar structure sets after expansion. At this stage, the mixture is still dense. It has flavor, sweetness, and malt character, but it does not yet contain the light honeycomb structure. That structure forms when the cooked mass is expanded. Gas generation or aeration creates tiny cavities inside the hot sugar malt mixture. The expanding gas pushes through the softened mass, forming a network of bubbles. The bubbles stretch the syrup into thin walls. As the mixture cools, those walls harden into a crisp, porous structure. The material changes quickly. A heavy syrup becomes a lighter foam-like mass. It is not soft like whipped cream. It is a hot sugar structure full of trapped voids. When it sets, it becomes brittle and dry. The expanded malt mass is cooled and broken down into smaller pieces. It may be formed into rough pellets, cut, screened, or milled into controlled fragments before shaping. The goal is to create center pieces that can be rounded into small balls of consistent size. The pieces pass through sizing equipment. Screens remove fines and oversized fragments. Airflow can pull away light dust. The accepted pieces move into rounding equipment. The centers tumble inside rotating pans or drums, where their edges are gradually worn down. Rounding is slow and mechanical. The rough pieces roll against each other and against the drum surface. Corners break away. Flat faces soften. Each piece becomes closer to a sphere. Small additions of binding material or syrup may help the particles build a smoother surface as they tumble. The center does not need to be perfectly polished yet. It only needs the right size, shape, and strength for chocolate coating. If the center is too rough, the chocolate shell becomes uneven. If it is too fragile, it will break during panning. If it is too dense, the final bite loses the light Maltesers texture. The rounded malt centers move through a drying and conditioning stage. Warm air reduces surface moisture and stabilizes the texture. The centers must be dry before chocolate is applied. Moisture would interfere with coating and could make the chocolate grip unevenly. Before coating, the centers are inspected and classified. Small broken pieces are removed. Oversized centers are separated. Dust is screened away. A clean, dry stream of malt balls then moves toward the chocolate panning area. Milk chocolate is prepared in a separate system. Cocoa ingredients, milk powder, sugar, cocoa butter, and vegetable fat or other formula components are mixed and refined. The mixture passes through rollers that grind the particles smaller. Refining gives the chocolate a smoother mouthfeel by reducing the size of sugar and cocoa particles. After refining, the chocolate is conched. In conching machines, heavy mixing arms continuously move the chocolate for a controlled time. The process smooths the texture, distributes fat around the dry particles, and develops the final flavor. The chocolate becomes glossy, fluid, and uniform. The chocolate must then be tempered. Tempering controls how the fat crystals form. The chocolate is cooled and gently reheated through a precise temperature curve. This creates stable crystals that help the coating set with a clean finish. Proper tempering gives the shell firmness and reduces dullness or soft texture. The malt centers enter coating pans. These are large rotating drums, angled so the centers tumble continuously. A measured amount of tempered milk chocolate is sprayed or ladled onto the moving centers. The chocolate touches the dry malt balls and spreads as they roll. The first layer is thin. It seals the porous center and creates a smoother surface for later layers. The centers continue tumbling while cool air passes through the pan. The chocolate sets around each piece. Once the layer is firm enough, another small addition of chocolate is applied. The coating builds gradually. Maltesers are not coated with one heavy pour of chocolate. The shell forms through repeated thin layers. Each layer must spread, set, and bond before the next layer arrives. This creates a rounded, even chocolate covering without flooding the centers or joining them together. The sound inside the pan changes as the shell thickens. At first, the centers make a dry rattling sound. As chocolate builds, the movement becomes softer and heavier. The pieces roll over one another with a smoother, duller sound. The pan speed, air temperature, chocolate temperature, and addition rate all control the shell. If chocolate is added too quickly, pieces stick together. If air is too cold, the coating can set before it spreads. If air is too warm, the surface stays tacky. The machine balances movement, temperature, and timing until each ball reaches the correct size. After the main chocolate coating is built, the pieces continue tumbling to smooth the surface. Small ridges are evened out by rotation. The shell becomes more uniform with every turn. The pieces are now recognizable as Maltesers, but they still need finishing. A polishing stage may apply a very thin finishing layer. The pieces tumble while a glazing or polishing material is added in tiny amounts. This gives the chocolate surface a smooth, lightly glossy appearance and helps reduce scuffing during packaging. The finished pieces then move into cooling. They travel through a cooling tunnel or controlled room where air removes heat from the shell. The chocolate firms fully. The coating becomes stable enough for weighing, conveying, and bagging. After cooling, the Maltesers pass through inspection. Screens remove broken pieces, dust, and double pieces stuck together. Metal detection checks the product stream. Optical systems can detect unusual shapes, exposed centers, dull patches, or oversized clusters. Rejected pieces are separated from the main flow. The accepted pieces move into holding hoppers above the packaging line. The hoppers are designed to keep the chocolate pieces moving gently. Sharp drops are avoided because the coating can scuff or chip. Controlled gates feed the product into weighing systems. Multi-head weighers portion the Maltesers into exact amounts. The pieces fall into small weighing buckets. The control system selects the best combination of buckets to reach the target weight. Gates open and the measured amount drops into the bagging machine. For small bags, packaging film unwinds from a roll. The film passes over a forming collar and wraps into a tube. A vertical heat seal closes the back seam. The weighed Maltesers drop into the open tube. Horizontal sealing jaws close the bottom and top seals, forming individual bags. The sealed bag passes under a coder. Production information is printed onto the film. The bag then moves through check weighing, Any underweight or overweight pack is rejected automatically. For boxed formats, the pieces may be weighed into a bag first, then inserted into a carton. Flat paperboard blanks are opened into box shapes. The filled inner pack slides inside. Folding rails close the flaps. Adhesive or locking tabs hold the carton shut. Twix begins as a long sheet of biscuit dough moving toward a cutting line. The dough is built to become a crisp base. It must be strong enough to carry caramel, but light enough to snap cleanly under the chocolate shell. The process starts with flour, sugar, fat, leavening ingredients, salt, and water entering a controlled mixing system. Dry ingredients are weighed first. Flour flows from storage bins through enclosed conveyors. Sugar and smaller powders are added through separate dosing units. Each ingredient passes into a mixer in measured amounts. The mixer does not simply stir the powders. It builds a dough with the right texture for sheeting, cutting, baking, and coating. Fat is added to create the short, crumbly biscuit texture. It coats part of the flour and limits gluten development. This is what helps the biscuit break cleanly instead of becoming chewy. Water enters slowly, just enough to bind the dry ingredients. The mixer blades fold, press, and turn the mass until it becomes a firm dough. The dough exits the mixer in heavy pieces. It is fed into a hopper above a sheeting machine. Large rollers pull the dough downward and compress it into a thick sheet. The sheet passes through more rollers, each pair reducing the thickness. The surface becomes smoother with every pass. The dough sheet must reach a precise thickness. If it is too thick, the biscuit will bake slowly and make the bar heavy. If it is too thin, it can crack under the caramel layer. The sheeter controls the height with adjustable roll gaps. Once the sheet is even, it moves under cutting rollers. The rollers score and cut the dough into long, narrow biscuit fingers. Small holes may be docked into the surface. Docking lets steam escape during baking and helps prevent the biscuit from puffing unevenly. The shaped dough pieces transfer onto an oven band. The band moves continuously through a long baking tunnel. Heat surrounds the dough from above and below. Moisture begins leaving the biscuit. The surface firms first, then the center dries and sets. Inside the oven, the dough changes from pale and soft to golden and crisp. The fat melts, water evaporates, and the structure becomes rigid. The biscuit pieces shrink slightly as they bake. Their edges sharpen, and the surface develops a light toasted color. The oven has different temperature zones. The first zone sets the shape. The middle zones drive off moisture. The final zones finish the color and texture. The goal is a biscuit that is dry, crisp, and strong enough for high-speed handling. The baked biscuit fingers leave the oven and enter a cooling section. Air flows over and under the pieces. Cooling is important because caramel cannot be applied properly to hot biscuits. If the biscuit is too warm, the caramel may spread too much or soften the structure. The cooled biscuits travel in straight lanes. Conveyor guides align them precisely. The next layer is caramel. Caramel is prepared in a separate cooking system. Sugar, glucose syrup, milk ingredients, fat, and water are mixed in heated vessels. The mixture starts as a pale liquid. As it cooks, water evaporates and the sugars concentrate. The liquid thickens and develops a smooth, stretchy body. The caramel must be cooked to a very specific texture. It cannot be too runny, or it will flow off the biscuit. It cannot be too firm, or it will not deposit evenly. The finished caramel must hold its shape as a layer, but remain soft enough to bite through. After cooking, the caramel is cooled to a controlled depositing temperature. It remains warm and pumpable. Pipes carry it to the depositor above the biscuit lanes. The depositor contains nozzles matched to the spacing of the biscuits. As each biscuit passes underneath, a ribbon of caramel is laid along the top. The caramel lands as a smooth strip, following the length of the biscuit. The depositor times each flow so the caramel starts and stops at the right point. It must not hang over the ends too far, because excess caramel can interfere with chocolate coating. The caramel-topped biscuits continue forward. Cooling air firms the caramel surface. The layer becomes stable enough to move, but it remains soft inside. The product now has the basic Twix structure: biscuit base and caramel top. Some lines form the biscuit and caramel as long continuous strips before cutting. In that version, caramel is deposited onto long biscuit slabs. The slabs then pass through slitting and guillotine cutting systems that divide them into individual bars. The cutting blades must pass cleanly through caramel and biscuit without dragging the layers out of position. The formed bars are spaced apart before chocolate coating. Correct spacing matters because the enrober must cover every side without bars touching each other. Vibrating conveyors and timing belts create even gaps between the pieces. Milk chocolate is prepared in another part of the factory. Cocoa ingredients, sugar, milk powder, cocoa butter, and fats are blended into a chocolate mass. The mixture is refined through rollers that reduce particle size. This gives the chocolate a smooth texture instead of a gritty one. The refined chocolate is conched. Heavy mixing arms move the chocolate for a controlled time. The mass becomes smoother, more fluid, and more uniform. The fat coats the dry particles evenly. The chocolate develops the proper flow for coating. Before it can cover the bars, the chocolate is tempered. Tempering controls the crystal structure of the cocoa butter. The chocolate is cooled and warmed through a precise temperature curve. Stable crystals form, allowing the coating to set with a firm surface and clean snap. The Twix bars enter the enrober on a wire mesh belt. A curtain of tempered milk chocolate falls from above. Each bar passes through the curtain and chocolate flows over the caramel top, down the sides, and around the biscuit edges. At the same time, chocolate is applied from below. The mesh belt allows chocolate to coat the underside. The bar becomes fully covered. Excess chocolate drains through the belt and returns to the tempering system. After the curtain, the bars pass under air blowers. These blowers remove extra chocolate from the top and sides. The airflow smooths the coating and controls shell thickness. Too much chocolate would make the bar heavy and uneven. Too little would expose biscuit or caramel. The coated bars then pass over a vibrating section. The vibration helps remove trapped air bubbles and evens the chocolate surface. The shell becomes smoother as the bar continues forward. The surface pattern forms as the chocolate settles. Twix bars often have a slight ripple or flow texture on top because the chocolate curtain, airflow, and movement shape the coating before it sets. The ridges are not carved after cooling. They form while the chocolate is still fluid. The bars enter a cooling tunnel. Inside, chilled air circulates around them. The chocolate shell begins to crystallize and harden. Cooling must be controlled carefully. If it is too fast, the coating can become dull or crack. If it is too slow, the chocolate may remain soft and mark during wrapping. As the bars move through the tunnel, the shell changes from glossy liquid to firm chocolate. The caramel stays enclosed. The biscuit remains dry because the coating seals it from the outside. At the end of cooling, the bars leave the tunnel fully set. They pass through inspection. Cameras check shape, size, coating coverage, and surface defects. Metal detectors scan the product stream. Bars with exposed biscuit, missing chocolate, broken edges, or distorted caramel are rejected automatically. Accepted bars move toward wrapping. Twix bars are usually packed as paired fingers or single bars depending on the format. Lane systems align the bars and bring them into the required grouping pattern. For a twin pack, 2 bars are placed side by side with controlled spacing. The wrapper begins as a roll of printed film. The film unwinds and passes through rollers that control tension. It moves around a forming box, where it wraps around the bar or bar pair. The product enters the film tube in perfect timing with the print registration. A longitudinal seal closes the film along the back or underside. Heated sealing wheels, or jaws, press the film layers together. Then cross-seal jaws close the ends of each pack. The jaws seal and cut at the same time, separating one wrapped pack from the next. Bounty begins with shredded coconut being turned into a compact, moist center. The coconut is the main structure of the bar. It does not start as a smooth paste. It starts as small white flakes with a fibrous texture. Each flake must be hydrated, sweetened, bound together, shaped into bars, covered with chocolate, cooled, wrapped, and packed without losing the soft coconut bite inside. The coconut arrives in dry, shredded form. It is stored in ingredient bins or bags before feeding into the mixing area. The flakes are light and irregular. Some pieces are longer, some are finer. The production system controls the blend, so the finished center has an even texture. Before mixing, the coconut may pass through screens. Oversized pieces are separated. Very fine dust can be reduced. The goal is not to make the coconut perfectly uniform, but to keep the texture consistent enough for forming. The center must hold together, but it still needs visible coconut fibers. A syrup phase is prepared separately. Sugar, glucose syrup, water, and milk-based ingredients are measured into heated vessels. The liquid warms as agitators turn. The sugar dissolves into the water and syrup base. The mixture becomes glossy and smooth. This syrup is the binder. It gives the coconut center sweetness, moisture, and shape retention. It must be thick enough to hold the flakes together, but not so thick that it forms a hard candy texture. The final bar needs a soft pull when bitten, not a brittle snap. Fat ingredients are added into the warm syrup system. They help create a creamy texture and reduce dryness in the coconut mass. The warm liquid becomes richer and more opaque as the fat disperses. Mixing keeps the binder even so no area becomes greasy or thin. The syrup is cooked to a controlled solids level. Water evaporates as heat continues. The mixture thickens slightly. The factory does not rely on appearance alone. Temperature, time, and flow controls keep the binder within the correct range. The shredded coconut then enters a heavy-duty mixer. The dry flakes drop into the bowl or continuous mixing chamber. The warm binder is added gradually. The mixer turns slowly at first, folding syrup into the coconut. Then the paddles increase their work, pressing and lifting the mass. The texture changes quickly. Dry flakes become damp. Loose coconut turns into a cohesive mixture. The white fibers become glossy as the binder coats them. The mass begins to clump, but the mixer prevents large lumps from forming. This is one of the most important stages in bounty production. If the coconut receives too little binder, the center will crumble. If it receives too much, the bar will feel sticky and heavy. If mixing is too rough, the flakes break down and the texture becomes pasty. The machine must combine the ingredients while preserving the fibrous coconut structure. The finished coconut mass is warm, moist, and thick. It cannot be poured like liquid. It must be pressed, extruded, or sheeted into the correct bar shape. The mass feeds into a forming machine. In one method, it is forced through a wide rectangular die as a continuous slab. Rollers or belts control the height and width. The surface is leveled as the coconut sheet moves forward. The sheet must be dense enough to stay together, but not compressed so hard that the center loses its softness. Another method forms the coconut mass into long ropes. The mixture passes through shaped openings, producing continuous bars with rounded edges. The ropes move on conveyors while cutting blades divide them into individual lengths. The forming system gives the center its basic profile. A bounty center is not flat like a biscuit base. It is thick, soft, and slightly rounded. The shape matters because the chocolate coating must flow over it evenly. Sharp corners would make thin chocolate spots. Smooth edges help the shell cover the bar completely. After forming, the coconut centers move into a cooling or setting section. Cool air firms the binder. The bars become easier to handle. The center does not become hard. It simply gains enough structure to survive transfer, spacing, and chocolate coating. The bars pass through alignment guides. They must travel in straight lanes with equal gaps. Uneven spacing would cause problems in the enrober. Two bars touching each other could become stuck together by chocolate. A bar out of position could miss part of the coating curtain. Chocolate preparation runs separately from the coconut line. Cocoa ingredients, sugar, milk powder for milk. Chocolate versions, cocoa butter, and other fats are combined into a chocolate mass. The ingredients are mixed until they form a thick paste. This paste passes through refining rollers that grind the sugar and cocoa particles down to a fine size. Refining changes the texture from gritty to smooth. The refined chocolate then moves into conching equipment. Large mixing arms or rollers work the chocolate for a controlled period. The mass becomes smoother and more fluid as fat coats the dry particles. Heat and movement develop the final flow behavior needed for coating. Before the chocolate can cover the coconut bars, it must be tempered. Tempering controls the cocoa butter crystals. The chocolate is cooled, stirred, and gently warmed through a precise sequence. This creates stable crystals that allow the shell to set firm, smooth, and glossy. The tempered chocolate is pumped to the enrober. The coconut centers approach on a wire mesh belt. The belt carries them beneath a falling curtain of chocolate. As each center passes through the curtain, chocolate pours over the top and runs down the sides. At the same time, chocolate coats the underside. The mesh belt allows chocolate to rise or be applied from below, so the coconut center is sealed all around. Excess chocolate drains through the belt and returns to the circulation system. The coating is not finished immediately after the curtain. The bars pass under controlled air blowers. These blowers remove excess chocolate and smooth the shell. They also help define the final coating thickness. The airflow must be strong enough to even the surface, but not so strong that it exposes coconut. The soft shape of the coconut center affects how the chocolate moves. The coating flows more easily over rounded sides than over sharp corners. It gathers slightly at the base before excess drains away. The wire belt supports the bar while leaving only fine contact marks underneath. The coated bars may pass over a vibrating section. The vibration releases trapped air bubbles and helps chocolate settle evenly. Small ripples smooth out as the bar continues forward. The shell becomes continuous around the coconut core. Some bounty formats are twin bars. In those lines, centers may be formed and coated as individual fingers, then later paired inside the wrapper. The spacing system keeps the fingers separated until the wrapping stage. Each piece must have its own complete chocolate shell before pairing. The coated bars enter a cooling tunnel. Chilled air flows around them as they move slowly through the enclosed space. The chocolate begins to crystallize. The liquid shine becomes a firmer surface. The shell sets without melting the coconut center or drawing moisture outward. Cooling must be balanced. If the tunnel is too cold, chocolate can contract too sharply and crack. If cooling is too slow, the bars may mark or deform before wrapping. The line controls air temperature, humidity, belt speed, and residence time. Kit Kat is assembled from a dry, crisp wafer core that is first strengthened and sealed by contact with a warm, fat-based filling, then coated in chocolate, then cooled so the wafer stays crunchy and the bar snaps cleanly on the finger lines. The wafer stream begins as a thin batter system that must bake into sheets with low moisture and uniform thickness. Flour is sieved to remove lumps and to stabilize hydration. Sugar and salt are weighed precisely because they affect browning and sheet brittleness. Water is tempered so batter viscosity stays consistent at the depositor. A small fat or emulsifier addition is used to control plate release and sheet texture. The batter is mixed only until smooth because excessive mixing increases gluten development and makes sheets tough and less crisp. Batter viscosity is one of the main controls because it determines how evenly the batter spreads on wafer plates. The batter is held in a feed tank with gentle agitation to prevent settling of flour fines. From there, it is pumped to wafer irons. Each iron is a pair of heated plates that close, bake, and open in a cycle. A metered dose of batter is deposited onto the plate and spreads under closing pressure. Heat drives rapid water evaporation and sets the starch matrix into a porous, brittle sheet. Bake time is tuned so the sheet dries to low moisture without scorching, because scorch creates bitter notes and weak zones. When the plates open, the wafer sheet is released and moved to cooling. Cooling stabilizes crispness and prevents warping. The sheet is then cut into finger-sized leaves. Cutting uses sharp rotary blades to avoid cracking edges. At this stage, the wafer leaves are extremely brittle and must be handled with low-impact conveyors and minimal drop heights to prevent breakage before lamination. Lamination creates the multi-layer wafer block that defines the bar bite. A thin layer of wafer creme is applied between leaves as an adhesive and moisture barrier. This creme is not the outer chocolate, but a fat-based filling designed to soak slightly into wafer pores and then set. The creme is prepared by blending sugar, cocoa components, milk powders, and fat into a smooth paste with controlled viscosity. Particle size is refined so it spreads evenly and does not feel gritty. The creme is held warm enough to flow, but not so warm that it becomes runny and floods the wafer. Assembly stacks alternating wafer leaves and cream layers. A depositor spreads cream onto a wafer leaf in a uniform film. Another leaf is placed on top, and the stack repeats until the target number of layers is reached. Alignment matters because misaligned leaves create uneven edges and weak points at the snap lines. Light compression follows stacking to ensure contact and eliminate air gaps. Compression must be controlled because excessive force crushes wafer cells and reduces crispness. After stacking, the wafer block enters a setting tunnel. This tunnel cools the block so the creme fat network crystallizes and locks the layers together. The block must become rigid enough for cutting, but not so cold that wafer becomes overly brittle and shatters. The setting profile is staged so the outer surfaces firm first and then the core equalizes. Once set, the block is cut into sticks and then into the familiar finger format. A longitudinal cutter slices the block into wide slabs. A second cutter defines the number of fingers per bar by cutting grooves or separating lanes. A cross cutter then creates bar lengths. Knife sharpness and speed are tuned to avoid crushing the wafer. Ultrasonic knives can be used in some lines to reduce drag through the cream layers and keep edges sharp. The cut wafer fingers are then routed into an enrobing sequence that is designed to seal the wafer from humidity. Chocolate or compound coating is prepared in a separate system where flow behavior must remain constant. The coating is melted and filtered. If real chocolate is used, it is tempered to create stable cocoa butter crystals so it sets with gloss and snap. If a compound coating is used, it is temperature controlled for viscosity and set rate. In either case, viscosity control is critical because it determines coating thickness and whether grooves between fingers fill correctly. Before the main enrobe, many lines apply an undercoat or pre-coat that improves sealing. A thin coat can be applied to the bottom first to reduce moisture migration from the environment into the wafer. The bars then pass through a curtain that coats the top and sides. Excess drains through a wire belt. Air knives remove excess and shape the surface. Air knife settings are tuned to avoid stripping too much coating from corners because exposed wafer edges absorb moisture quickly and lose crispness. If the bar is intended to have fully defined finger lines, the coating flow must not bridge the grooves excessively. Groove definition is managed by coating viscosity, curtain temperature, and belt speed. Too thin a coating leaves exposed edges. Too thick a coating floods grooves and reduces snap separation. The process targets a thickness that seals the wafer while still preserving the break lines. After coating, the bars enter a cooling tunnel. Cooling is staged to set the surface quickly so it does not slump. Then, to crystallize the full thickness without stress. Stable crystallization prevents bloom and keeps the surface firm for wrapping. Tunnel humidity is controlled to prevent condensation because moisture on the surface can cause haze and can also migrate into wafer through microcracks before the coating fully sets. During cooling, the wafer core is also protected from moisture changes. The internal creme acts as a barrier and binds wafer layers, but the wafer will still soften if the coating does not seal fully. The combination of internal creme saturation and external coating seal is what maintains the distinctive, crisp bite. A properly set bar has a rigid, layered core that fractures sharply and a coating that breaks cleanly rather than smearing. Inspection follows cooling. Vision systems check coating coverage, groove definition, and edge exposure. Weight checks confirm stick length and coating mass. Bars with broken fingers or exposed wafer are rejected because they will soften faster and package poorly. Rework handling separates wafer material from coating material because wafer pieces cannot be remelted like coating. Wrapping is designed to maintain a low moisture environment. Bars are fed into flow wrappers that form film around each unit and seal it. Seal integrity matters because moisture ingress softens wafer and destroys snap. Film tension is controlled so it does not scuff the coating or snap fingers. Print registration keeps graphics aligned with the bar orientation. Coating is applied for traceability. Wrapped bars are collated into multi-packs or cartons. Collation systems handle bars with minimal impact to avoid cracking finger edges. Cartons add protection against compression that would fracture wafers. Cases are packed and palletized. Storage temperature stability keeps coating crystals stable and reduces the risk of bloom and softening. Corny-style cereal bars are manufactured by first engineering a binder that will set at room temperature, then using that binder to lock cereals and inclusions into a compressed slab, then cutting, coating, and wrapping fast enough to preserve crunch and prevent stickiness. The process starts with the binder kettle because everything downstream depends on how that syrup flows, how fast it sets, and how much moisture it brings into the cereal phase. Sugar and glucose syrup are metered into heated tanks and pumped to a cooker. Water is added in controlled quantity because it affects dissolution and final viscosity. If fat is part of the recipe, it is melted separately and held at a stable temperature so it can be injected precisely. If the bar includes honey or malt extracts, those streams are heated just enough to pump without degrading aroma. Cooking raises solids and defines the set behavior. The syrup is heated to dissolve sugars fully and drive off water to a target concentration. Concentration is monitored by temperature and by inline density because the binder must land in a narrow window. Too wet and the finished bar becomes sticky and soft, and it can weep into the wrapper. Too dry and the binder becomes glassy and the bar turns hard and prone to fracture. Residence time is controlled to prevent overbrowning because browning changes flavor and also increases viscosity unpredictably. Once the syrup reaches endpoint, it is cooled slightly to a mixing temperature where it will coat dry ingredients without scorching them. This is the moment when flavors and sensitive components are added. Vanilla and fruit aromas are injected late to preserve volatiles. Acid additions are kept minimal and are dosed as solutions when used, because acidity changes inversion rate and can shift stickiness over time. Emulsifiers can be added to keep fat dispersed in the binder and to improve wetting of cereal surfaces. Dry ingredients are prepared in parallel, and their particle size distribution is treated as a structural parameter. rolled oats are screened to remove fines that would increase dust and create dense patches. Crisped rice or wheat crisps are screened to remove broken fragments because fragments fill voids and reduce crunch. Nuts and seeds are sized to a narrow band, so they distribute evenly and do not punch through the slab. Dried fruit pieces are conditioned to avoid hard clumps because clumps create weak bonding zones and tear during cutting. Chocolate chips or compound drops are stored cool, so they hold shape and do not smear during mixing. Dry blending begins by assembling cereals and inclusions in a low-shear mixer. The mixer is designed to distribute without crushing crisps. Mixing time is short because every extra minute creates more fines by abrasion. The blend is staged in a feed hopper that meters a consistent mass flow into the wet mixing step. Consistent flow is important because binder dosing is tied to dry mass rate. Wet mixing is where the binder and dry blend are joined. The hot binder enters through a manifold that spreads it across the mixer width rather than dumping it in one spot. Paddles fold the dry blend through the binder so every particle is coated. This stage must be fast because the binder is cooling and thickening continuously. If mixing is too slow, the binder sets in patches and leaves dry pockets. If mixing is too aggressive, crisper components break and the bar loses its light texture. Temperature control is the main stabilizer during wet mixing. Binder must be warm enough to flow and coat. It must not be so hot that it softens chocolate drops or makes fruit pieces smear. The dry blend must not be cold enough to shock the binder and cause premature thickening. Many lines temper the dry blend slightly so the combined mass stays within a workable temperature range for forming. Once the mass is uniform, it is delivered immediately to a forming line. Forming begins with depositing the sticky mass onto a moving belt between side rails that define width. A spreader distributes the mass across the belt and a pre-compression roller evens thickness. The mass then passes under a main compression station. Compression is the defining mechanical step for a cereal bar. It determines density, bite, and cut quality. Compression is controlled by roller gap and pressure. A tighter gap yields a denser bar that holds together strongly and cuts with clean edges. A looser gap yields a lighter bar with more visible cereal structure, but can crumble. Compression must also avoid crushing cereal completely. Crushing generates fines that absorb binder and create hard zones. The line tunes compression so the binder bridges particles, while the cereal retains its internal porosity. After compression, the slab enters a setting tunnel or cooling zone. This zone brings the binder through its set transition. If the binder is sugar heavy, it will transition toward a glassy state as it cools, and water activity stabilizes. If the binder includes fats, it will also set as fats crystallize. The tunnel profile is staged so the slab firms gradually. Rapid cooling can create a hard skin while the interior is still warm and mobile, which leads to warp and internal separation. Setting is also where moisture management is locked in. If the binder retains too much moisture, it will migrate into cereal and soften it over time. If it is too dry, it will continue to pull moisture from fruit inclusions and make them tough. The process targets a moisture equilibrium that keeps cereal crisp and fruit pliable. This is achieved by binder solids, fruit conditioning, and tunnel conditions. Cutting follows once the slab reaches a cuttable firmness. Cutting is usually two-stage. A longitudinal cutter trims edges and splits the slab into lanes. A cross cutter then makes bar lengths. Knife selection is important because the slab contains hard inclusions. Dull knives tear the slab and pull cereal out, creating ragged ends. Sharp guillotine blades or rotary knives slice cleanly. Ultrasonic blades can be used to reduce drag through sticky binder and to keep inclusions from catching. Trim is handled carefully because cereal bar trim can be reintroduced only within limits. Trim contains more fines and has different binder distribution. Too much trim increases density and reduces crunch. Rework ratios are therefore controlled so the product remains consistent. After cutting, the bars can be coated or decorated. If the format includes a chocolate base, a tempered or controlled viscosity coating is applied to the bottom. Bars pass over a coating roller that lays down a uniform film. Excess is stripped to a target thickness. A cooling tunnel sets the coating so it does not smear in wrapping. If a drizzle is applied, nozzles deposit lines across the top, while the base is still tacky enough to bond. Nut or crisp toppings can be added during this tack window. Some products include a wafer layer or a milk compound layer. In those cases, the forming line adds that layer either before compression or after cutting. The same principle applies. The additional layer must not introduce moisture that would soften cereal. Adhesion must be strong enough to survive wrapping without delamination. Before packaging, bars pass through final stabilization. This step equalizes temperature so condensation does not occur inside wrappers. It also allows coatings to reach full set and resist scuffing. Bars are then inspected for weight, length, and coating coverage. Broken bars and off-size bars are rejected because they create crumbs and contaminate seals. Packaging is designed around moisture barrier performance because cereal bars lose crunch quickly if they absorb humidity. Bars feed into flow wrappers that form film around each unit and heat seal it. Seal temperature and dwell are tuned so seals are tight without heating the bar enough to soften binder or melt coatings. Film tension is controlled because excessive tension can crack coatings or deform the bar edges. Coating is applied for traceability. If bars are packed in multi-packs, individually wrapped units are collated and then overwrapped or cartoned. Cartons add crush protection and reduce bending damage. Case packing stacks. Cartons in patterns that limit compression. Storage conditions are controlled so bars do not experience temperature swings that can cause fat bloom on coatings or moisture migration inside the bar. Mars bar manufacture is a timing problem disguised as a candy problem because three materials with very different behavior must arrive at the cutter with the same firmness and then accept a chocolate coat without distortion. The sequence is easiest to understand from the point where the finished bars enter the chocolate curtain. At that moment, the centers must be dry to the touch, straight and dimensionally stable. If they are even slightly warm or soft, the curtain and air knives will round edges and create thin spots. The plant therefore builds the center as a slab, locks its structure by staged cooling, and only then exposes it to chocolate. Chocolate for enrobing is prepared first in process terms because the enrober is sensitive to viscosity drift. Chocolate is melted, filtered, and moved into a tempering loop. Tempering establishes a seed crystal population, so the coating sets fast with gloss and stable snap. Working temperature is held tightly because small shifts change curtain thickness and final coat weight. The chocolate recirculates through the enrober and is filtered to keep crumbs from building up and roughening the surface. While chocolate is being held ready, the bar center is built upstream as two layers. The lower layer is an aerated nougat, and the upper layer is a caramel sheet. These layers are not cooked together because they need different concentration endpoints and different set behavior. Nougat begins with a syrup that defines solids and elasticity. Sugar and glucose syrup are metered and cooked to a specific concentration. The cooker is run to an endpoint that supports a light chew once the mass is aerated. Too high a moisture content produces a soft slab that cannot be cut cleanly. Too low a moisture content produces a tight nougat that loses its light character. The cooked syrup is cooled slightly, so it can be combined with a foam phase without damaging it. The foam phase is produced separately as a protein solution that is aerated under controlled shear. Airflow rate and back pressure are used to fix bubble size distribution. Density is monitored continuously because it becomes the direct knob for bar weight and bite. Fine bubbles are preferred because they resist coalescence and create a uniform interior. Syrup and foam meet in a continuous folding mixer. Folding distributes syrup through the foam while preserving bubble structure. Heat from the syrup strengthens bubble walls and helps lock the microcell network. Fat is injected as a thin stream to soften texture and reduce stickiness. If the nougat is chocolate flavored, cocoa components are introduced in a way that avoids sudden viscosity jumps, often as a pre-dispersed stream rather than dry powder dumped into the foam. The aerated nougat is then deposited as a continuous slab onto a moving belt. A depositor spreads it to width and leveling rollers set thickness. Thickness is controlled tightly because it defines the core height and influences cooling time. Immediately after deposition, the slab enters a cooling tunnel with staged zones. Early zones firm the surface so it can support caramel later. Later zones reduce internal temperature gradually so the slab does not form a brittle skin over a soft interior. Caramel is produced in parallel as an elastic, high solids mass. Sugar and glucose syrup are cooked with dairy components to develop caramel notes and reach a solids endpoint that yields chew rather than glass. Fat is added near the end to smooth texture and reduce tack. The caramel is then cooled to a working temperature where it can be deposited as a sheet without running. It is held in jacketed tanks with gentle agitation to prevent a surface skin and keep temperature uniform at the depositor. Layering occurs when the nougat slab arrives at the caramel station at the correct firmness. Caramel is applied as a continuous layer using a slot depositor. A smoothing bar spreads the caramel and fixes thickness. The temperature relationship between nougat and caramel is critical. Nougat must not be warm enough to compress under the caramel head. Caramel must not be hot enough to melt the nougat surface. The interface must bond strongly because cutting will pull on it. After caramel deposition, the combined slab is conditioned again. Cooling at this stage is aimed at making the caramel cut stable. If caramel is too warm, it smears and sticks to blades. If too cold, it can crack, especially at the edges. Cooling is staged to avoid differential contraction between nougat and caramel that would create curl. Once the slab reaches the cutting firmness window, it moves into trimming and portioning. Edge trim removes uneven slab edges and creates a uniform width for lane cutting. Trims are handled as rework in controlled ratios because rework carries different temperature history and can change texture if used too heavily. Rotary knives cut the slab into long lanes. A cross cutter then slices lanes into bar lengths. Cutter timing is synchronized to belt speed, so each bar has consistent mass. Knife surfaces are managed to prevent caramel buildup that would tear edges. The cut centers are then separated and aligned for enrobing. Transfer sections are designed with minimal drop height because impacts can dent nougat and shear caramel. Spacing is controlled so bars do not bridge in the chocolate curtain. Many lines apply a brief pre-chill here to firm surfaces and reduce deformation under the curtain. Pre-chill is balanced so it does not create condensation when the bars enter warmer chocolate zones. Enrobing coats each center with chocolate on top, sides, and bottom. A top curtain covers the bar, and a bottoming system lays a base layer beneath it. Excess chocolate drains through the wire belt. Air knives shape the coating and control the foot. Air knife pressure is tuned so it removes excess without exposing corners, especially where caramel edges can create sharp transitions. If a surface pattern is applied, it is added immediately after the curtain while the coating is still tacky. A stringer deposits thin lines, and then the bars enter the cooling tunnel. Cooling after enrobing is staged to set the chocolate without stress and without bloom. The first zone sets the surface quickly so the coating does not slump and so the bars can be handled. Subsequent zones cool more gradually to promote stable crystal growth. Tunnel humidity is controlled to prevent condensation that would dull the surface. Bars exit at a temperature suitable for wrapping with coating hard enough to resist scuffing. Inspection occurs after cooling. Vision checks look for exposed edges, thin spots, and misshapes. Weight checks verify that cutting and coating remain stable. Rejects are diverted. Chocolate rework is remelted and returned upstream through the tempering loop. Nougat and caramel rework is handled separately because aeration and moisture history affect its behavior. Wrapping begins when the bars are fully set. Flow wrappers form film around each bar and seal it with controlled heat and dwell time. Film tension is managed so it does not scuff the coating. Coating is applied. Wrapped bars are collated into multi-packs or cartons and case packed. Reese's peanut butter cups are manufactured by building two materials that behave in opposite ways and then forcing them to meet cleanly at high speed. The chocolate must flow like a liquid in the depositor, then crystallize into a rigid shell that releases from tooling. The peanut center must be soft enough to bite with a short crumble, yet stiff enough to hold shape, resist oil separation, and accept a top seal without squeezing out. The peanut component begins with roasted peanuts that are converted into a paste with tightly controlled temperature. Incoming kernels are cleaned and screened, so shell fragments and fines are removed before grinding. Roasting level is chosen to drive down moisture and develop aroma while keeping oils stable. After roasting, the nuts are cooled quickly so residual heat does not thin the paste and accelerate oil separation during storage. Grinding is staged because peanut butter texture depends on particle size distribution and shear history. A coarse grinder breaks kernels and releases oil, creating a continuous fat phase. A second grinder refines particles to the desired smoothness. Friction heats the paste, so grinders are jacketed or throughput is controlled to keep temperature in a narrow range. If the paste warms too much, it becomes overly fluid and later produces a filling that flows and smears. If too cool, it becomes stiff and resists blending with dry powders. The paste then moves into filling formulation. The goal here is not a spreadable peanut butter, but a depositable confection that sets with a slightly crumbly bite. Fine powdered sugar is the main structure builder. It is sifted so clumps are removed because clumps create dry pockets and inconsistent dosing. Salt and flavor components are prepared as micro additions. A compatible fat stream may be used to tune firmness and melt profile, and emulsifiers are staged to stabilize the oil phase and improve flow through depositors. Mixing is done in high torque equipment because the peanut paste thickens dramatically as powders are added. The paste enters first, then powders are introduced in a controlled feed so the mix wets gradually rather than forming dry rafts. As sugar absorbs free oil, the mass becomes less glossy and more plastic. Mixing energy is tuned to avoid turning the mass into a smooth, homogeneous paste. Too much shear breaks the short structure and yields a slick filling that feels less crumbly. Too little shear leaves dry streaks and causes weak spots that crack under the chocolate cap. Temperature control during filling mixing is a core lever. The mass must be warm enough that it can be pumped and metered, but not so warm that it relaxes and spreads inside the cup. Jacketed mixers and conditioned hoppers hold the filling in a narrow temperature band. The filling is often moved through a short conditioning step after mixing so fat crystals can begin forming and the texture becomes more consistent. This conditioning also allows entrained air to rise out. Large bubbles create voids that later collapse and cause dents in the top surface. While the filling is being prepared, the chocolate system is built for shell formation. Chocolate is melted, filtered, and held at a stable temperature, so viscosity is constant. The key operation is tempering. which establishes a controlled population of stable cocoa butter crystals. Tempered chocolate behaves like a fluid at the depositor, but solidifies quickly into a glossy, firm structure. Tempering is maintained by staged cooling and reheating within a continuous unit, with sensors watching temperature and flow resistance as indirect signals of crystal content. The forming line starts with paper liners. Liners are denested and placed into cavities on a moving mold plate. Cavity fit is controlled because the liner must be supported to prevent wrinkling when chocolate is spun. Liner placement accuracy matters because a shifted liner creates thin shell walls on one side and thick walls on the other, which leads to breakage during demolding and uneven bite. Shell formation is done by depositing a metered shot of tempered chocolate into each lined cavity and then immediately shaping it into a cup. The shaping step is usually a spin or a combination of spin and vibration. Spinning forces chocolate up the liner walls and leaves a hollow center. Spin time and speed define wall thickness and rim height. If the spin is too aggressive, walls become too thin and crack later. If too gentle, the shell becomes heavy and reduces space for filling. Vibration during or after spinning helps remove bubbles and smooth the interior surface. The newly formed shells enter a brief cooling zone. This is not full hardening. It is a partial set that makes the shell self-supporting but still receptive to bonding with the filling. Cooling must be controlled because an overly cold shell can create poor adhesion and delamination. An overly warm shell can deform when filling is deposited and can create uneven rim geometry. Filling deposition is engineered to place a consistent puck inside the shell without contaminating the rim. The filling is delivered from conditioned hoppers to deposit heads that meter precise volumes. Depositing can be a single shot that forms a dome or a spiral that levels more evenly. The deposit height is controlled so there is clearance for the chocolate top. If filling touches the rim, it interferes with sealing and creates weak edges. Many lines use a light vibration or a short dwell to let the filling settle into a consistent profile, but the motion must be gentle because too much vibration can smear filling into the shell wall and create uneven thickness. Top sealing is created by depositing a second shot of tempered chocolate. The chocolate must flow outward enough to meet the shell rim and form a continuous bond. Deposit volume sets top thickness. Too thin a top can crack during handling. Too thick a top dominates bite and slows cooling. Some lines apply a short vibration after topping to level the surface and release trapped air. This vibration is tuned to avoid chocolate climbing the liner edge and creating flash. Once topped, the cups enter the main cooling tunnel. Cooling is staged because chocolate crystallization must be guided into a stable form. The first zone sets the surface quickly to prevent smearing and to lock the top shape. Subsequent zones cool more gradually so the entire chocolate mass crystallizes uniformly without internal stress. Exit temperature is chosen so the cups are rigid enough to demold and convey without scuffing. During cooling, the filling also stabilizes. Fat crystals within the peanut mixture continue forming and the filling becomes firmer and more brittle in its short structure. This is essential for the characteristic bite. If the filling remains too soft, it will squeeze under pressure and cause top separation. If it becomes too hard, it loses the expected crumble and becomes a dense block. Demolding releases the lined cups from the mold plate. Release depends on correct temper and correct cooling because the chocolate must contract slightly away from the cavity walls. Gentle ejectors or inversion steps drop the cups onto belts. Handling is kept low impact because rims can chip and liners can crease. Once on the belt, cups can pass through inspection stations. Vision checks can detect missing tops, off-center fills, and liner misplacement. Weight checks confirm dosing accuracy and flag missing deposits. Packaging is designed around preventing temperature rise and abrasion. Individual cups are often flow-wrapped. Wrapping film is formed around each cup and sealed with controlled heat and dwell time. Heat must be sufficient to seal film without warming the chocolate surface enough to mark. Film tension is controlled so it does not crush the cup. For multi-pack formats, cups are collated into trays or sleeves that prevent movement and protect rims. Cartoning then adds stiffness and stack strength. Case packing arranges cartons to reduce compression and minimize vibration that could crack chocolate edges. Skittles are manufactured by making a chewy center that behaves like a resilient pellet, then growing a hard sugar shell around that pellet in hundreds of small additions, then adding color and a final finish so every piece looks identical and moves cleanly through packaging. The center is engineered first as a thermoplastic candy rather than as a syrup. Sugar and glucose syrup are treated as structural ingredients that control glass transition and chew. Granulated sugar is screened so crystal size stays consistent and dissolution is predictable. Glucose syrup is held warm in jacketed tanks so it meters smoothly and does not pulse. Water is filtered and tempered because small temperature changes affect the cook profile. Acids and salts are staged as micro additions because they influence both flavor and how the cooked mass behaves during conditioning. A dissolving step makes a clear feed syrup. Sugar and water are mixed under heat with strong agitation until no grain remains. Any undissolved grain would later seed crystallization and create weak spots in the center. The clear syrup then enters a continuous cooker or batch cooker where it is concentrated to a high solids level. Heat input is rapid to minimize time at elevated temperature because long heat exposure darkens sugars and shifts texture. In many lines, the syrup is heated under pressure and then finished with a flash step that removes water quickly and tightens final moisture. Cook endpoint is chosen to produce a mass that can be shaped without sticking and without cracking. If moisture is too high, pellets deform and flatten during later tumbling. If moisture is too low, pellets become brittle and can fracture under coating impacts. The cooked base is therefore delivered to a cooling stage that drops temperature to a range suitable for adding sensitive components. Flavor for the center is not the same as the final flavor experience because much of Skittles' character is carried by shell and aroma at the surface. Even so, the center is commonly given a base flavor note and a consistent sweetness profile. Flavors are injected after the hottest zone to preserve volatiles. Acids may be split between center and shell strategy. A portion of acid can be added late to set a baseline tartness without weakening the center structure. Mixing downstream uses static mixers or low shear manifolds to avoid entraining air. The cooked mass then becomes a plastic dough and enters forming. Forming begins by pushing the mass through an extrusion head that produces ropes at a fixed diameter, or by delivering it directly to a pellet former, depending on equipment design. Rope diameter is a major variable because shell thickness is added on top, so the core size must stay tight to hit final piece size. A synchronized knife cuts the rope into pellets. Cut timing is locked to belt speed, so pellet mass stays consistent across the run. Fresh pellets have cut faces and a warm surface. They are transferred immediately to a rounding stage where they tumble and roll. Rolling knocks off sharp edges and produces the characteristic rounded shape that will coat evenly. This stage also seals micro cracks at the surface by gentle friction warming. Rounding is tuned to avoid smearing because smearing creates flats that later show as uneven shell thickness. After rounding, the cores go through conditioning. Conditioning is a controlled cooling and rest that stabilizes temperature and moisture through each core. The cores must be firm enough to withstand repeated coating cycles, but the surface must still accept initial shell adhesion. Conditioning airflow and temperature are set so surfaces are dry to the touch, while the interior retains the desired chew. Shell building is performed in rotating coating pans or perforated drums. The drum creates a rolling bed of cores that continuously cascades. Cascade behavior is controlled by fill level and rotation speed. A stable cascade ensures every core sees the same exposure to syrup spray and drying air. If the bed slides rather than rolls, pieces develop flat faces and shell becomes uneven. The first shell layers are engineered as a bonding bridge. A relatively light syrup is sprayed in short pulses. Droplet size is kept fine, so the film spreads thinly and evenly. Dry air immediately follows to evaporate water and begin crystallization. These early coats must set quickly to prevent pieces sticking together, and they must not add enough water to soften the core surface. Once the first layers lock on, bulk shell growth begins. A higher solid syrup is sprayed, and fine sugar is often dusted onto the wet surface. The dust absorbs moisture and accelerates set while increasing build rate. Airflow then dries the layer and forces crystallization. This spray, dust, and dry cycle is repeated many times. Each cycle adds a tiny increment of thickness, so stress remains low and cracks do not form. Drying is the most sensitive control in shell growth because it governs how crystals form within each layer. If drying is too fast, the surface can harden while moisture remains inside the layer, creating a trapped core that later pits or fractures. If drying is too slow, the surface stays tacky and pieces can twin. Twin formation is prevented by matching spray volume to drying capacity and maintaining continuous rolling so wet surfaces do not remain in contact. As thickness increases, the process shifts to smoothing. Powder addition is reduced, and the system relies more on thin syrup films that flow into micro valleys. Longer dry times then lock a smoother surface. Smoothness matters because it improves shine and prevents scuffing, and it provides a better substrate for printing. Color is applied as a sequence of thin coats rather than a single heavy dye layer. Color solutions are prepared to precise concentration and filtered so no particulates enter spray nozzles. Color is introduced when shell thickness is near target, so pigment remains close to the surface and looks bright. The drum receives a light color spray, then drying air sets it fully. Multiple passes build saturation evenly. Heavy color application would pool and create blotches, especially where shell microtexture is still present. Because Skittles are produced in multiple colors, runs are typically separated by color. Each color run uses its own color dosing and its own endpoint checks. Between colors, spray circuits are flushed to prevent cross tint. Shade is monitored by optical measurement on samples, and adjustments are made by changing pass count or concentration rather than by altering the underlying shell build. After color, clear finishing coats can be applied to improve durability and reduce rub-off. These coats are very light and followed by longer drying to reach a stable moisture endpoint. Moisture endpoint is critical because a slightly damp shell scuffs and sticks, while an overly dry shell can become brittle and chip under impact. The letter marking is applied near the end of finishing. Printing uses edible ink, transferred by a pad or similar contact method. Pieces are fed into a system that presents a stable face and applies the mark. Surface condition at this moment matters. The shell must be smooth and dry so the ink bonds and does not smear. A short drying stage follows, so the mark sets before pieces rub against each other. Polishing is the final surface operation. A very small amount of polishing agent is misted onto the tumbling pieces. The film spreads through contact and fills micropores, increasing gloss and reducing friction. Reduced friction helps pieces flow through packaging machines and reduces scuffing in bags. Polishing is controlled carefully because excess film can feel waxy and can interfere with print clarity. After polishing, the pieces are conditioned briefly to equalize moisture and temperature. Equalization reduces internal stress in the shell and improves resistance to fine cracking. Screening then removes fines, broken pieces, and twins that escaped earlier control. Size classification can be used to remove out-of-band pieces that would stand out in packs and behave differently in weighers. Packaging begins with gentle conveying into multi-head weighers. The pieces must flow freely without bridging. Hopper design and surface finish reduce sticking. The weigher selects combinations of small hopper dumps to hit target weight quickly. The portion drops into a form-fill seal machine, where film is formed into a tube and sealed above and below the product drop. Seal timing is set so candies do not lodge in the seal zone. Clean seals are essential because moisture ingress softens shells and dulls gloss. For tube or carton formats, dosing can be by count or by volume, but the same requirement applies. Piece size distribution must be tight so count accuracy stays high and so packs feel consistent. After filling, closures are applied and coating is printed. Packs are checked for weight and seal integrity, then case packed. Milka chocolate is manufactured by turning cocoa and dairy ingredients into a low moisture, fat continuous suspension with a very narrow particle size range, then setting that suspension into bars through precise crystal control and staged cooling. The line begins by stabilizing dairy inputs because milk solids introduce both flavor and a strong sensitivity to water. Milk arrives as powder, concentrate, or a pre-processed dairy ingredient depending on the plant setup. powdered streams are sieved to break agglomerates because compacted milk lumps do not disperse evenly and later show up as grainy flecks. If liquid dairy or concentrate is used, it is filtered and held at controlled temperature, so viscosity and dosing remain stable. Sugar is handled as a dry engineered solid, screened for consistent crystal size, because crystal size determines refining load and final mouthfeel. Cocoa components enter as cocoa liquor, cocoa butter, and sometimes cocoa powder. Cocoa liquor is kept warm so it stays pumpable, while cocoa butter is melted and filtered so it meters cleanly. A key upstream objective is removing free water from the system early because water drives chocolate thickening and unstable flow. When the process uses a crumb route, milk and sugar are combined and cooked into a dry matrix before they ever meet the final chocolate fats. The milk-sugar mixture is heated under controlled mixing, so sugar dissolves and water evaporates. As water leaves, the mix transitions from syrupy to granular, and then to a dry crumb. Endpoint is set by moisture content and by how the crumb fractures. Too wet yields a crumb that later makes chocolate seize and thicken. Too dry yields excessive browning and harsh cooked notes. Once the crumb reaches endpoint, it is cooled and milled to a manageable particle size, so it blends uniformly downstream. If the process does not use a crumb route, the same moisture goal is achieved by strict control of powder moisture and by downstream conching, but the plant still treats water as the enemy of stable rheology. All ingredient handling and air exposure is therefore designed to keep humidity pickup low. Mixing creates the first chocolate mass. Cocoa liquor and a portion of melted cocoa butter enter a mixer to form a fluid fat phase. Crumb or milk solids and sugar are then introduced gradually, so particles become wetted rather than floating as dry islands. The mixer uses high torque and wall scraping because the mass is thick at this stage. The target is a uniform paste where solids distribution is even and there are no dry pockets. This paste is not yet smooth, but uniformity here prevents downstream refining streaks. Refining is where smoothness is physically created. The paste is fed to roll refiners or an equivalent milling system that reduces particle size into the low tens of microns. Roll refining squeezes the mass through a series of narrowing gaps, breaking sugar crystals and milk solids into smaller particles. The output leaves the final roll as thin flakes. These flakes have very high surface area and very little free fat at their surfaces, so they behave dry and dusty unless they move quickly into the next stage. Conching transforms refined flakes into a stable flowing chocolate by completing fat wetting and removing trace moisture. In a conch, paddles or rotors knead the chocolate under controlled heat. Mechanical work breaks down remaining agglomerates and forces cocoa butter to coat every particle. Heat keeps fats fluid, while airflow carries away moisture and volatile compounds. Moisture removal is not optional because even a small amount of water pushes viscosity up sharply. Conching is therefore run as a controlled balance between temperature, shear, and venting, so the mass becomes fluid without overheating. During early conching, the mass can appear crumbly and resistant because particle surfaces are not fully wetted. As conching continues, friction drops and the mass becomes glossy and pumpable. Viscosity and yield stress are the process indicators because they determine whether the chocolate will deposit cleanly into molds and whether it will release cleanly after cooling. Emulsifiers are introduced late in conching to fine-tune flow. Lecithin reduces yield stress by improving particle wetting. Additional flow modifiers can be dosed to reduce viscosity further at the same fat content. Dosing is precise because tiny changes alter curtain behavior, depositor accuracy, and final snap. Once conched, the chocolate is held in tempered storage tanks at a stable temperature with gentle agitation. Filtration removes any unmelted lumps or foreign particles before tempering. At this point, the chocolate is chemically and physically ready, but its fat crystals are not yet in the correct form for molding. Tempering is the controlled crystallization step that makes the final bar glossy, hard, and stable. Cocoa butter can solidify into multiple crystal forms, but only specific forms produce the desired contraction and snap. Tempering machines First, heat the chocolate enough to melt all existing crystals. They then cool it under agitation so crystals nucleate. The chocolate is then reheated slightly to melt unstable crystals while leaving stable seed crystals. The output is a chocolate that remains fluid at the working temperature but contains a measured population of stable seeds. This seeded chocolate feeds molding. Molds are cleaned and temperature conditioned so the surface is dry and does not shock the chocolate. Deposit heads meter chocolate into each cavity with tight mass control. Immediately after deposit, molds pass over vibrating tables. Vibration releases trapped air bubbles and levels the surface so the bar face is smooth. Vibration also helps chocolate flow into fine embossed details if the mold carries a design. Cooling tunnels then set the chocolate. Cooling is staged because the goal is to crystallize the entire bar without creating stress. The first zone sets the surface quickly so it holds shape. Subsequent zones cool more gradually so stable crystals grow through the thickness. If cooling is too fast, internal stress can lead to cracks or later bloom. If cooling is too slow, throughput drops and the chocolate may stay soft long enough to pick up marks. Air humidity is controlled in the tunnel to prevent condensation because moisture on the surface can cause sugar bloom and dullness. As the bar cools, it contracts slightly. This contraction is essential for demolding. Correct temper and correct cooling create a bar that releases cleanly when the mold is inverted or flexed. After release, bars move onto conveyors that minimize scuffing. Any surface abrasion at this stage will remain visible after wrapping. Inspection can be integrated immediately after demolding. Vision checks can detect surface voids and broken corners. Weight checks confirm deposit accuracy. Bars outside tolerance are diverted. Reworked chocolate is collected and remelted, then returned upstream in controlled proportions so it does not destabilize tempering. Wrapping protects the finished bars from moisture, oxygen, and physical marks. Bars are indexed into wrapping machines that fold film or foil around them. Fold geometry is controlled so the wrap sits tight without crushing edges. Heat sealing parameters are tuned to close the film without warming the bar enough to soften the surface. Coating is applied for traceability and packs are checked for seal integrity. Cartoning and case packing follow for multi-unit formats. Cartons provide stacking strength and protect wrapped bars from puncture and abrasion. Cases are built and sealed for transport. Storage temperature stability is maintained to protect the cocoa butter crystal network because temperature swings can encourage bloom and soften snap. The Snickers process is organized around synchronization because nougat sets by cooling, caramel sets by concentration and cooling. Peanuts must be applied while the caramel surface is at the right tack, and chocolate must be tempered so it locks into a stable crystal form. Each stream, therefore, has its own preparation and holding system, and the assembly belt is timed so every stream meets the slab within a narrow temperature window. Nougat begins as an aerated structure that must remain stable through cutting and enrobing. A cooked syrup stream provides the solid backbone. Sugar and glucose syrup are metered and concentrated to a target solids level in a cooker. The cook is run to a defined endpoint because solids control the final resilience. Too much water leaves a weak slab that deforms under knives. Too little water yields a tight chew that resists cutting and can fracture at edges. The syrup leaves the cooker and is conditioned to a blending temperature that supports foam locking without scorching. A separate foaming stream is generated from a protein solution. The solution is mixed to a consistent concentration and fed into a continuous aerator. Air is metered into the aerator, and shear is used to create fine bubbles. Bubble size distribution is controlled because it determines uniform bite and density stability. Density is monitored continuously because density becomes the direct control for final bar weight and mouthfeel. The syrup and foam merge in a continuous mixer designed for folding rather than beating. Folding distributes hot syrup through the foam while preserving the bubble network. Heat partially sets the protein films around bubbles and increases structural strength. Fat is injected as a thin stream to soften texture and reduce stickiness. Emulsifiers can be dosed to stabilize the air-fat sugar system and to control viscosity at the depositor. The mixed nougat exits warm and plastic with a defined density. Nougat deposition converts this aerated mass into a continuous slab. The depositor lays down a wide band onto a moving belt. A leveling station sets thickness. Thickness control is critical because it defines the core height and impacts later coating ratio. The slab enters a staged cooling tunnel. Early zones remove heat enough to support the next layer without collapse. Later zones firm the interior without creating a hard skin that could crack during cutting. The slab leaves cooling firm, but still slightly compliant, so it bonds to caramel. Caramel is prepared in parallel as a high solids elastic layer. Sugar and glucose syrup are cooked with milk components to develop flavor and reach a targeted solids endpoint. This endpoint determines whether the caramel behaves as a cohesive sheet or as a smear. Fat is added to smooth the matrix and reduce stickiness at knives. The caramel is cooled to a working temperature where it can be deposited as a continuous layer without running. It is held in jacketed tanks with gentle agitation to prevent a surface skin and to keep temperature uniform. Peanuts are prepared as a dry size graded topping stream. Roasted peanuts are screened to remove fines and broken bits. Size distribution is tightened so surface coverage is consistent and peaks are limited. Tall peaks create coating thin spots in the chocolate curtain. Peanuts are cooled after roasting so they do not warm the caramel surface and reduce tack control. The nut stream is held dry so it remains free-flowing at the spreader. Layering starts when the nougat slab reaches the caramel station. Caramel is applied as a continuous sheet using a slot depositor or ribbon head. A smoothing bar spreads the caramel and locks thickness. The temperature relationship between nougat and caramel is controlled. The nougat surface must be stable enough to carry the caramel without compressing. The caramel must be warm enough to wet the nougat surface and bond. If caramel is too hot, it can melt the nougat surface and create a weak interface. If too cool, it can sit on top and delaminate later. Nut application happens immediately after caramel deposition. A spreader distributes peanuts across the width in a controlled mass flow. The peanuts land on a caramel surface that is still tacky enough to hold them. A light pressing station can embed peanuts slightly to improve mechanical lock. Pressing is carefully limited so it does not crush nuts into fragments and does not force caramel to squeeze sideways. The layered slab then passes through a conditioning zone. This zone firms the caramel surface and stabilizes nut position before cutting. Cooling is staged to avoid stress between nougat and caramel because the two layers contract differently. The slab must reach a firmness that cuts cleanly. If too warm, caramel smears and drags. If too cold, caramel can crack around nuts and create weak zones under the chocolate. Edge trimming removes uneven slab edges. Trim is collected for controlled rework streams based on moisture and temperature. The main slab enters a lane cutter that slices it into long ropes. Rope width defines final bar width. A cross cutter then slices ropes into bar lengths. Cut timing is synchronized to belt speed to keep bar mass consistent. Knife surfaces are managed because caramel and nut fragments can build up and create ragged cuts. Clean cuts reduce exposed crumb that would contaminate the chocolate system. Bar centers are transferred to the enrobing line with controlled spacing. Spacing prevents chocolate bridges. Transfer points minimize drop height because impact can dislodge peanuts and can dent the nougat. A brief pre-chill can be used to stiffen the surface and improve chocolate flow behavior. The pre-chill is balanced so it does not cause condensation when entering the chocolate area. Chocolate coating is produced and tempered in a dedicated loop. Chocolate is melted and filtered. Tempering then creates stable cocoa butter seed crystals through controlled cooling and reheating. Working temperature is held in a narrow band so viscosity remains stable at the curtain. Viscosity control is essential because it sets coating thickness and therefore final weight and bite. Enrobing applies chocolate as a curtain over the top and sides with a bottoming system for the underside. Bars pass under the curtain on a wire belt. Excess drains through the belt. Air knives remove excess and shape the surface. Air knife settings are tuned to avoid exposing nut peaks at corners while still controlling the foot at the base. A stable curtain and consistent belt speed keep coating uniform across the run. If a surface pattern is required, it is added while the coating remains tacky. A stringer drizzles thin lines that bond to the base coat. The bars then enter the cooling tunnel immediately. Cooling is staged to set the chocolate without stress and to lock nuts into the coating. The first zone sets the surface quickly so the coat does not slump and so peanuts stop shifting. Later zones cool more gradually to promote stable crystal growth and reduce bloom risk. Tunnel humidity is controlled to prevent condensation and surface haze. Bars exit cooling at a temperature where the chocolate is hard enough for wrapping without scuffing. Inspection follows cooling. Vision systems detect exposed edges, bald spots, and coating splits. Weight checks confirm portion control across cutting and enrobing. Bars outside tolerance are diverted. Chocolate rework is remelted and returned upstream, while nougat and caramel rework streams are handled separately because their aeration and moisture differ from fresh mass. Wrapping begins with a flow wrapper that forms film around each bar and seals it. Seal temperature and dwell are tuned, so seals are tight without overheating the chocolate. Film tension is controlled to avoid scuffing. Code printing adds lot and date marks. Wrapped bars are then collated into multi-packs or cartons and case packed. Bounty bars are manufactured by turning desiccated coconut into a cohesive moist center with a controlled chew, shaping that center into bars, sealing it with tempered chocolate, then cooling and wrapping while moisture and fat migration are kept stable. The production logic starts with coconut water management because the center is engineered to feel moist without releasing liquid into the chocolate coat. The plant, therefore, treats coconut solids, sugar syrup, and fats as a binding system that must land in a narrow water activity window. Desiccated coconut arrives as a dry particulate with variable flake size. It is screened to remove fines and oversized pieces. Fines can make the center pasty and reduce the fibrous bite. Oversized pieces can tear through the chocolate coat and create weak points. The coconut is conditioned in controlled humidity storage so it does not pick up moisture unevenly, because uneven moisture produces streaks in center firmness. Sugar syrup is prepared in parallel. Granulated sugar is dissolved in heated tanks with agitation until the solution is clear. Glucose syrup can be added to control crystallization and to keep the center from becoming gritty. Syrup concentration is controlled by density. Too dilute a syrup makes the center wet and prone to weeping. Too concentrated a syrup makes the center dry and crumbly after cooling. A fat stream is prepared to chew and to carry flavor. Vegetable fat is melted and held at a defined temperature, so viscosity is stable for metering. Emulsifiers can be staged to help distribute fat through the syrup and to improve binding to coconut fibers. Flavor. Additions are prepared as concentrates that can be injected late, so aroma remains strong. Center mixing begins by building a binder phase. Warm syrup and melted fat are blended into a uniform liquid. The blend temperature is chosen so the binder wets coconut quickly but does not cook it. If the binder is too hot, it can soften coconut structure and reduce bite. If too cool, it thickens and coats poorly, leaving dry coconut pockets. Coconut is then introduced into the binder in a high-torque mixer. The mixer uses folding action to pull coconut through the binder and coat every particle. Mixing energy is tuned to avoid shredding coconut flakes into fines. The mass transitions from loose dry flakes to a cohesive, moist mixture as syrup fills voids and fat coats fibers. The endpoint is judged by uniform gloss and consistent torque with no visible dry streaks. Moisture control is enforced at this stage by controlling binder ratio and mixing residence time. Coconut absorbs binder and then slowly releases free syrup if overloaded. The line, therefore, targets a ratio where the mixture holds shape when compressed but does not bleed liquid. This stability matters because free syrup would dissolve sugar at the chocolate interface and cause separation later. Once mixed, the coconut mass is conditioned. Conditioning equalizes temperature and allows binder to distribute through the fiber network. It also lets any entrained air rise out. Air pockets are undesirable because they create voids that collapse during enrobing and cause dents in the coating. Conditioning is often done in a feed hopper with gentle agitation to keep the mass uniform while avoiding further breakdown of flakes. Forming converts the coconut mass into bar centers. A common method uses extrusion. The mass is fed into an extruder that compresses it and pushes it through a rectangular die. Compression removes air and densifies the center to a consistent bulk density. Die dimensions set width and height. Belt. Speed is synchronized with extrusion output to prevent stretching because stretching changes density and later chocolate ratio. As the extruded ribbon exits the die, it enters a cutting station. A guillotine or rotary knife cuts the ribbon into bar lengths. Cut timing is locked to belt speed to maintain consistent weight. Knife geometry is designed to slice cleanly through fibrous coconut without dragging. If the mass is too warm, it smears at the cut. If too cool, it fractures and sheds crumbs. The line holds a narrow temperature window to produce clean edges. Some formats form the center by compression molding rather than extrusion. In that route, the coconut mix is portioned and pressed into cavities. Pressing controls density and surface smoothness. The pressed pieces release and move to coating. The process goal remains the same. The center must be dimensionally stable and consistent in moisture. Before chocolate coating, the centers are preconditioned. Preconditioning firms the surface so it resists deformation under the chocolate curtain. It also stabilizes surface moisture so the chocolate bonds without encountering wet spots. Cooling air is controlled because overly cold centers can cause condensation, and that moisture will create bloom or adhesion defects. Chocolate coating is prepared in a separate tempering loop. Chocolate is melted and filtered. Tempering creates stable cocoa butter seed crystals through controlled cooling and reheating. Working temperature is maintained tightly because viscosity determines coating thickness and because temper drift causes bloom and weak snap. Coating viscosity is adjusted by temperature control and by cocoa butter balance. Enrobing applies chocolate to the coconut centers. Centers pass through a chocolate curtain that coats the top and sides. A bottoming system coats the underside so the center is fully sealed. Excess chocolate drains through a wire belt. Air knives shape the coat and control the foot. Air knife. Settings are tuned to avoid exposing coconut fibers at corners. Exposed fibers wick moisture and can trigger surface defects. Because coconut centers can shed fine particles, crumb management is integrated into the enrober. Centers are screened or air cleaned before coating to remove loose coconut dust. The chocolate loop uses filtration to remove any carried particles that would create specks or roughness. Stable filtration prevents buildup that would change curtain quality. After enrobing the bars, enter a cooling tunnel. Cooling is staged to set the chocolate surface quickly and then crystallize the interior of the coat gradually. Rapid surface set prevents slumping and preserves bar shape. Gradual cooling reduces internal stress and reduces bloom risk. Tunnel humidity is controlled to prevent condensation because condensation causes sugar bloom and dullness. While the coat sets, the coconut center continues to equilibrate. The binder fat begins to crystallize and locks chew. Moisture distribution stabilizes across the center. The chocolate coat becomes a barrier that slows moisture exchange. The interface between center and coat is sensitive to fat migration. If the center fat is too mobile, it can migrate into the chocolate and soften it. The formulation and the cooling profile are therefore tuned so center fat is solid enough at storage temperature to remain in place. If the product includes a decorative chocolate drizzle, it is applied immediately after enrobing while the base coat is still tacky. A stringer deposits thin lines across the top. The bars then enter the cooling tunnel, so both layers crystallize together. Inspection follows cooling. Vision systems check for exposed corners and coating voids. Weight checks confirm portion control across forming and coating. Bars with dents or broken corners are rejected. Rework handling is separated for chocolate and for coconut center. Chocolate rework is remelted and retempered. Coconut center rework is blended back only within controlled ratios because moisture and density can differ from fresh mix. Wrapping begins once bars reach a stable handling temperature. Bars feed into flow wrappers that form film around each unit and heat seal it. Seal temperature and dwell are tuned, so the seals are strong without heating the chocolate enough to scuff. Film tension is controlled so it does not abrade the chocolate surface. Print registration aligns graphics. Date coding is applied for traceability. Wrapped bars are collated into multipacks or cartons depending on format. Collation uses lanes and gating to group bars without impact. Cartons are erected and loaded and closed. Finished packs are case-packed and palletized. Mars bars are manufactured by building an aerated nougat foundation, laying down a caramel layer that bonds without smearing, coating the assembled centers in tempered chocolate, then cooling and wrapping once all layers reach stable handling strength. The line is designed around rheology transitions rather than ingredients. Nougat begins as a warm foam that must become a cuttable slab. Caramel begins as a hot, elastic melt that must become a clean sheet. Chocolate begins as a fluid suspension that must crystallize into a stable shell. Each stage is managed by temperature windows and residence times that keep those transitions repeatable. Nougat construction starts with a syrup that defines solids and elasticity. Sugar and glucose syrup are metered into a cooker and concentrated to a target solids level. The cook is short and controlled because long exposure deepens color and shifts viscosity. Solids endpoint controls whether the final nougat feels light or tight. A syrup that is too wet yields a center that compresses and deforms under cutting. A syrup that is too dry yields a center that becomes chewy and resistant. A separate aeration stream provides the bubble network. A protein solution is mixed to a defined concentration and fed into a continuous aerator. Airflow is metered and rotor speed sets bubble size distribution. Density control is continuous because density directly determines bar weight and perceived lightness. Fine uniform bubbles are preferred because they resist collapse and create a smooth bite. The hot syrup stream merges with the foam stream in a continuous folding mixer. Folding is used to distribute syrup without shredding bubbles. Syrup heat strengthens the bubble walls and helps lock the structure. Fat is injected as a thin stream to soften texture and reduce stickiness. Emulsifiers can be introduced to improve stability and to tune flow at the depositor. If a chocolate note is required in the nougat, cocoa components are added in a way that avoids sudden viscosity spikes, often by dispersing them into a small fat stream before injection. The aerated nougat leaves the mixer as a warm plastic mass with controlled density. It is deposited onto a moving belt as a wide slab. A spreader head and gauge rollers set thickness tightly. Thickness matters because it defines the bar cross-section and affects cooling time. the slab moves through a cooling tunnel with staged zones. The early zones firm the surface so it can accept the next layer without collapsing. The later zones pull heat out more gradually, so the interior sets without creating a brittle skin. Caramel production runs in parallel with a different set of constraints. Caramel is cooked from sugar, glucose syrup, and dairy components to an elastic solids endpoint. That endpoint is chosen so the caramel forms a sheet and cuts cleanly. Too low solids yield smear and squeeze. Too high solids yields cracking and glassy bite. Fat is added to smooth texture and reduce tack on knives. The finished caramel is cooled to a working temperature where viscosity is stable. It is held in jacketed tanks with gentle agitation to prevent a surface skin and keep the temperature uniform across the run. Layering is where the two streams must meet in the right state. The nougat slab enters the caramel station at a temperature that is firm but receptive. Caramel is deposited as a continuous layer using a slot head or ribbon head. A leveling bar spreads the caramel to a consistent thickness. The temperature difference between caramel and nougat is controlled, so the interface bonds without melting the nougat surface. If caramel is too hot, it can soften the nougat and create a weak interface. If caramel is too cool, it can sit on top and separate during cutting. After layering, the slab is conditioned again. This conditioning step firms the caramel so it becomes cut stable. Cooling is staged to avoid differential contraction between layers. Differential contraction can create curl or separation lines. The target exit condition is a slab that holds shape, has a firm caramel surface, and can pass through knives without drag. Edge trimming removes slab edges where thickness variation is most likely. The trimmed material is collected for controlled rework streams. The main slab is then cut into lanes with rotary knives. Lane width sets bar width. A crosscutter slices each lane into bar lengths. Cut timing is synchronized with belt speed to control weight. Knife temperature and surface finish are managed because caramel can adhere and cause tearing. Clean cutting reduces exposed nougat pores that can trap air and later create coating voids. The cut centers are transferred onto the enrobing line with controlled spacing. Spacing prevents chocolate bridges. Transfer points minimize drop height because nougat can dent and caramel can shear. A short pre-chill can be used to firm the surface and improve coating behavior. Pre-chill is balanced so the center does not become so cold that condensation forms when it enters the chocolate area. Chocolate coating is prepared in a tempering loop. Chocolate is melted and filtered. Tempering creates stable cocoa butter seed crystals by controlled cooling and reheating. Working temperature is held tightly because viscosity defines curtain thickness and final coating mass. If viscosity rises, the bars gain weight and corners can become bulky. If viscosity drops, the bars can show thin spots and exposed edges. In robing coats, the bars using a top curtain and a bottoming system. Bars pass through the curtain on a wire belt. The underside is coated by a chocolate bath or roller that lays a continuous base. Excess chocolate drains away. Air knives smooth the surface and define the foot. Air knife settings are tuned to remove excess without exposing corners, especially where caramel edges can create sharp transitions. A stable curtain requires steady chocolate temperature and steady pump flow. If a surface pattern is required, a stringer applies chocolate lines while the base coat remains tacky. The pattern must bond and then set without smearing. The bars then enter the cooling tunnel immediately. Cooling sets the chocolate and stabilizes the whole bar. The first zone sets the surface quickly so the coating does not slump, and so the bar can be handled. The next zones cool gradually, so stable crystals form and bloom risk is reduced. Tunnel humidity is controlled to prevent condensation. Exit temperature is chosen so the coating is hard enough for wrapping without scuffing. During cooling, the internal layers equilibrate. Nougat firms further as fats crystallize and bubble walls become more rigid. Caramel reaches its final elastic state. The chocolate coat becomes a barrier that slows moisture exchange and protects texture through storage. Inspection occurs after cooling. Vision systems check for coating voids and exposed edges. Weight checks confirm that cutting and coating remain stable. Bars outside tolerance are diverted. Chocolate rework is remelted and retempered. Nougat and caramel rework streams are managed separately because aeration and moisture history affect how they behave if recycled. Wrapping begins once bars are stable. Flow wrappers form film around each bar and heat seal it. Seal temperature and dwell time are tuned, so seals are strong without heating the chocolate enough to mark. Film tension is controlled, so it does not abrade the surface. Print registration aligns graphics and coding adds lot information. Wrapped bars are collated into multi-packs or cartons, then case-packed and palletized. Handling downstream is designed to avoid warm zones that soften chocolate and to avoid vibration that scuffs wrappers. Ferrero Rocher is manufactured by assembling a layered sphere where a roasted hazelnut sits inside a wafer shell. The shell is filled with hazelnut chocolate cream. Then the whole piece is coated in chocolate and rolled in chopped hazelnuts before a final set and wrap. The process starts with hazelnut preparation because nut size and roast level define the center bite and also influence how the coating adheres. Raw hazelnuts are cleaned with screens and air separation, so stones and shells are removed. The nuts are graded by diameter, so the center nut fits the wafer cavity without forcing cracks. Roasting line heats the nuts to a target color and moisture. Roasting drives off water and develops aroma while keeping the nut interior crisp. After roasting, the nuts are cooled quickly, so residual heat does not soften the wafer later. Skins are removed after roasting because loose skin fragments create bitter specks and interfere with cream texture. Nuts pass through rubbers or abrasive rollers that loosen skins. Air aspiration lifts skins away from the heavier nut kernels. The cleaned nuts are then rescreened to remove broken pieces. Whole nuts are routed to center insertion. Broken nuts are routed to chopped nut streams or paste production. A portion of the roasted nuts is chopped for the outer layer. Chopping is done with calibrated cutters that create a narrow size band. The target size must be large enough to read as crunchy pieces. The target size must be small enough to adhere evenly to a wet chocolate surface. Chopped nuts are screened to remove fines because fines create dust and dull the finish. The chopped nut stream is held in dry, conditioned air so it remains free-flowing. Another portion of the roasted nuts is processed into hazelnut paste for the cream and chocolate phases. Nuts enter a grinding system where rollers or stone mills reduce them to a smooth paste. Grinding generates heat, so the paste line uses temperature control to avoid over-thinning. The paste is refined until particle size is below the gritty threshold. The paste is then held in jacketed tanks with slow agitation to prevent oil separation. Wafer production runs as a separate stream because wafer must be crisp and dimensionally stable. Wafer batter is prepared by blending flour with water and sugar and small amounts of fat. Mixing is controlled to hydrate flour while limiting gluten development. The batter is filtered to remove lumps that would block depositor nozzles. Batter viscosity is adjusted so it spreads evenly on heated plates. Wafer baking uses wafer irons that form thin sheets by heating both sides. The batter is deposited onto the plates and spread into a uniform film. Heat drives water out quickly and sets the wafer into a rigid, porous sheet. Baking time is tuned so the sheet dries to low moisture without scorching. The sheet exits and is cooled so it becomes crisp and easy to cut. To create the Rocher shell, The wafer is shaped into cups or hemispheres. One method presses warm wafer sheets into molded cavities and then trims the edges. Another method bakes wafer directly into formed shapes using shaped plates. Forming must avoid cracks because cracks allow cream leakage. The formed halves are inspected by size and by edge integrity. Wafer halves are then paired into hollow spheres. A joining step applies a thin line of adhesive cream or chocolate along the rim. Two halves are aligned and pressed together. Pressure is controlled so the seam closes without crushing the wafer walls. The joined shells are cooled briefly so the seam sets and the sphere stays rigid during filling. The filling cream is produced as a fat-based emulsion with suspended solids. Sugar and milk solids are blended with hazelnut paste and cocoa components depending on the target profile. The mass is refined so it becomes smooth and spreadable. Refining can be done with roll refiners or ball mills that reduce particle size. The cream is then conched or mixed under heat to remove moisture and to distribute fat. Final viscosity is tuned so it can be dosed into wafers without air gaps. Chocolate used for coating is prepared and tempered for stable crystallization. Chocolate is melted and filtered to remove unmelted particles. Tempering cools the chocolate and builds stable seed crystals. The chocolate is then brought to a working temperature that maintains flow. Viscosity is adjusted by temperature control and by cocoa butter balance. Stable viscosity is needed because coating thickness must be consistent. Filling the wafer sphere begins by dosing a layer of cream into the cavity. The dosing head inserts into the shell opening and dispenses a controlled volume. The shell rotates or indexes, so cream spreads along the inner wall. This creates a base that will hold the center nut. The volume is controlled to avoid excess that would squeeze out at closure. A whole roasted hazelnut is then placed into the center. Placement uses a singulation system that feeds nuts one by one. Each nut is aligned and dropped into the cream bed. The cream supports the nut and locks it in position. Nut placement must be centered so the final sphere balances during coating. Off-center, nuts create wobble and uneven chocolate thickness. After nut placement, the cavity is topped off with more cream. The second dose surrounds the nut and fills remaining void volume. The dosing profile is tuned to avoid trapping air around the nut. Air pockets can collapse during cooling and cause surface dents. The cream surface is leveled, so the opening can be sealed cleanly. Sealing closes the filled sphere, so the cream is enclosed. A wafer cap or a chocolate plug can be applied depending on design. If a wafer cap is used, it is bonded with a thin film of cream and pressed into place. If a chocolate plug is used, tempered chocolate is deposited to create a seal. The seal must be strong enough to survive later tumbling and coating. After sealing, the filled spheres are cooled to firm the cream. Cooling brings the fat phase into a stable crystal state. It also reduces cream tack, so spheres do not stick during transfer. Cooling is staged, so wafer does not absorb condensation. Humidity control matters because wafer crispness must be preserved. Once the centers are stable, the line moves into chocolate enrobing. The spheres pass through a chocolate curtain or a dipping system. Chocolate coats the surface and also acts as the adhesive for chopped nuts. Excess chocolate drains off as the spheres roll on a wire belt. A controlled vibration can smooth the coating and release trapped bubbles. Air knives can trim excess and define a consistent thickness. Immediately after chocolate coating, the spheres enter a nut coating stage. Chopped hazelnuts are applied while the chocolate is still wet. The spheres roll through a bed of chopped nuts, or nuts are showered from above. Rolling ensures full coverage across the sphere. Nut feed rate is tuned, so coverage is dense but not clumped. Excess nuts fall away and are recirculated after screening. Nut adhesion depends on chocolate temperature and set speed. If chocolate sets too fast, nuts will not embed fully and will shed later. If chocolate sets too slow, nuts can slide and form bare patches. The process balances chocolate temper and cooling tunnel entry so the surface remains tacky long enough for nut embedding. After nut application, the pieces enter a cooling tunnel that solidifies the chocolate. The cooling profile is staged to promote stable crystals. Early cooling sets the surface quickly, so nuts lock in place. Later cooling pulls heat out, gradually, to avoid contraction cracks. Final exit temperature is set, so pieces are hard enough for wrapping. During cooling, the internal cream also equilibrates. The cream-fat network continues crystallizing and becomes firmer. This improves bite and reduces oil migration. Temperature stability prevents bloom risk and keeps the outer finish glossy. The wafer remains protected because the chocolate and cream act as moisture barriers. Some lines apply a final polish to reduce loose nut dust. A gentle tumbling or airbrushing step can remove unattached fragments. This step improves pack cleanliness and reduces debris in wrappers. It also reduces scuffing during downstream handling. Sorting and inspection occur before packaging. Vision systems can detect incomplete nut coverage and shape defects. Weight checks confirm fill and nut presence. Rejects are diverted so only uniform pieces reach wrapping. Metal detection can be used as a final integrity control. Cadbury chocolate begins as a controlled blend of cocoa components, dairy components, sugar, and fat that is refined into a smooth suspension, conched to stabilize flow and flavor, tempered to lock in stable crystals, then molded and packed, while temperature and viscosity stay inside a narrow window. Production starts with cocoa raw materials that arrive as beans or as processed cocoa ingredients, depending on the plant layout. When beans are used, they are cleaned first with screens and air separation, so stones and husk fragments are removed. The beans are then roasted in a programmed heat curve that drives off moisture and develops cocoa aroma while keeping scorch risk low. Roasting also makes the shells brittle, so separation is efficient later. After roasting, the beans are cracked and winnowed. Cracking breaks beans into nibs without pulverizing shells into fines. Winnowing uses airflow to lift lighter shell away from heavier nib. The nib stream is screened to remove oversized fragments that would strain grinders and to remove dust that would darken and overheat during milling. Nibs then enter grinding to become cocoa liquor. Grinding is a staged reduction where particle size drops while fat from the nib makes the mass flow. Early mills break nib into paste. Later mills refine the paste into a smoother liquor. Temperature is controlled because friction can raise heat and drive off aromatics. The goal is a stable liquor that is pumpable and consistent in solids and fat. Cocoa butter and cocoa powder streams are also managed. Cocoa butter is melted in jacketed tanks and filtered so no solid flakes remain. Cocoa powder is sieved to remove lumps that would create specks. These cocoa streams become levers for viscosity and flavor. More cocoa butter increases flow and melt. More cocoa solids increase intensity and thickness. Milk ingredients are prepared with the same attention to moisture and particle behavior. Milk powder is stored dry and sieved to break clods. Whey powders or lactose powders are handled similarly when used. These powders carry dairy flavor and also influence sweetness and caramel notes during later heating. Moisture in dairy powders must be low because water in chocolate drives thickening and seizing. Sugar is prepared as a clean, dry crystal feed. It is screened to control crystal size and remove agglomerates. Crystal size influences refining load and final mouthfeel. Fine sugar can reduce refining time but can increase dust and handling issues. Coarser sugar can slow refining and increase wear. The line selects a sugar specification that supports consistent refining performance. The first assembly stage is mixing, which creates a uniform pre-blend before refining. Cocoa liquor and melted cocoa butter enter a mixer and create a fat, continuous base. Sugar and milk powders are added gradually so they are wetted rather than floating as dry islands. Mixing uses a strong folding action to distribute powders through fat. The goal is a crumbly paste or thick dough depending on the recipe and the amount of fat present at this stage. In some milk chocolate processes, a crumb step is used to build characteristic dairy notes and to stabilize the milk solids. Crumb production combines milk and sugar with cocoa liquor or cocoa components and then heats the mixture to drive off water and develop flavor. The mixture is cooked until it becomes a dry or semi-dry crumb material. The crumb is then milled and later remelted into chocolate mass. This approach changes flavor and texture because it sets milk sugars in a different thermal history. Whether crumb is used or not, the downstream steps still require refining and conching. Refining is the step that turns the mixed paste into a smooth eating texture. Refining reduces the size of sugar and cocoa and milk particles so the tongue cannot detect grit. This is often done with 5-roll refiners or with alternative milling systems. In DUR, roll refining the paste passes between rollers with decreasing gaps. Each pass squeezes and shears particles smaller. The output becomes thin flakes because the mass leaves the final roll as a film that breaks off. Refined flakes have low free fat at their surface and are prone to holding moisture and air. They must be processed immediately into conching. Conching is a combination of mixing, shear, and controlled heat that changes both flavor release and rheology. In conching, the flakes are worked in a conche where paddles or rotors knead the mass. Heat keeps fat fluid and encourages volatile removal. Shear coats particles fully with fat, which reduces friction and lowers viscosity at a given fat level. Conching is often described as 2 overlapping goals. One goal is flavor smoothing by driving off unwanted volatiles and distributing aroma compounds. The second goal is flow control by reducing moisture and breaking down agglomerates so the chocolate becomes a stable suspension. Moisture control is critical because even small water content can cause thickening. Conches, therefore, manage airflow and temperature so water leaves gradually without overheating. During conching, emulsifiers can be added to fine-tune flow. Lecithin is a common flow modifier and it reduces yield stress by improving particle wetting. Another emulsifier can be used to reduce viscosity further at the same fat level. These additions are dosed late because early addition can mask conching effects and can change shear behavior. Dosing is precise because small changes alter how chocolate runs through pumps and through molding heads. After conching, the chocolate is held in storage tanks with gentle agitation. Tanks keep temperature stable, so the chocolate remains fluid. Agitation prevents separation and keeps the suspension uniform. Filters remove any foreign particles or unmelted lumps before tempering. At this stage, the chocolate is smooth and flavored, but it is not yet in the right crystal state for molding. Tempering is the controlled crystallization of cocoa butter that creates a stable set and a clean snap. Chocolate contains cocoa butter that can crystallize in several forms. Only specific forms give the desired gloss and contraction. Tempering builds a population of stable seed crystals and then holds the chocolate at a working temperature where these seeds guide solidification. Tempering is done in continuous tempering machines that heat and cool the chocolate in stages. The chocolate is first heated to melt existing crystals fully. It is then cooled while being agitated so crystals begin to form. It is then gently reheated to melt unstable forms while keeping stable seeds. The output is a chocolate that flows well, but contains the right crystal seeds. Process control uses temperature sensors and viscosity signals to maintain stability. Once tempered, the chocolate is ready for shaping. For bars, the main shaping method is molding. Polycarbonate molds move under deposit heads that meter chocolate into each cavity. The depositor fills to a precise mass because bar weight must be consistent. Molds then pass onto a vibrating table. Vibration removes trapped air bubbles and levels the surface. It also helps chocolate flow into sharp corners and improves surface gloss. After vibration, molds enter a cooling tunnel. Cooling is staged so the surface sets without shock. As chocolate cools, it contracts slightly. This contraction helps release from the mold. Cooling zones remove heat gradually so internal stress remains low. If cooling is too fast, the bar can warp or show bloom later. If cooling is too slow, throughput drops and molds remain occupied. When bars have solidified, they are demolded. Molds are flexed or tapped so bars release cleanly. The bars then move to inspection conveyors. Vision systems can detect surface defects and missing corners. Weight checks can confirm deposit accuracy. Defective bars are diverted for rework. Rework. Chocolate is collected and remelted, then reintroduced upstream in controlled ratios, so crystal history does not destabilize tempering. If the product includes inclusions like nuts or crisp pieces, the process adds an inclusion stage. Inclusions are prepared by roasting or drying and then screening to a tight size band. They are added either into the chocolate before molding or sprinkled into molds before depositing. Inclusion dosing must be consistent because it affects bar thickness and cooling time. Inclusion surfaces must be dry because moisture causes thickening and can create voids. If the product includes layered fillings, the line uses sequential depositing. A chocolate shell may be deposited first and partially set. A filling is deposited next. Another chocolate layer seals the top. This creates a composite bar that requires additional cooling time and more careful temper control. Even then, the same fundamentals apply. Each phase must flow at the right viscosity and set in the right order. Once bars are fully set, they move to wrapping. Wrapping is a mechanical process that protects chocolate from oxygen and moisture and from handling marks. Bars are fed into a flow wrapper or into a fold wrap system depending on the pack style. The wrapper forms film around the bar and makes seals. Seal temperature and dwell are controlled so the film closes without wrinkles. Film tension is controlled so it does not crush the bar edges. Toffee is manufactured by assembling a layered piece in a fixed cavity sequence, where a caramel cup is formed first, a hazelnut is seeded into that cup, a hazelnut cocoa cream is deposited around the nut, and a final chocolate cap is applied before cooling and tray packing. Production starts with preparing the two high-volume mass streams that define the piece. One stream is a caramel that must be firm enough to hold a cup shape, yet soft enough to bite cleanly. The other stream is a nut cream that must be smooth and pumpable, yet stable enough to keep its shape around the nut. A third stream is tempered chocolate for the cap and for any sealing functions. Caramel manufacturing begins with sugar and glucose syrup handling. Sugar is screened so crystal size is consistent and clumps are removed. Glucose syrup is held in jacketed tanks, so viscosity stays stable for accurate pumping. Dairy components are prepared as a controlled liquid or powder stream depending on the recipe design. Fat is melted and filtered so it can be metered smoothly into the cook. Cooking is done in a continuous cooker or a batch kettle that is designed for high solids confectionery. The syrup phase is heated to dissolve sugar and drive off water. Solids level is the key target because it controls final chew and flow at the depositor. If solids are too low, the caramel will slump in the mold and stick in tooling. If solids are too high, the caramel becomes glassy and cracks when formed into thin walls. Temperature and residence time are tuned so browning develops to the desired level without scorching. As the cook reaches endpoint, the caramel is cooled to a working temperature where it remains plastic. Cooling is staged, so viscosity is stable across the run. The caramel is held in a jacketed tank with gentle agitation to prevent skin formation. This tank feeds the forming depositor through heated pipes that avoid cold plugs. Flow meters and pressure sensors keep the depositor feed steady. Hazelnut handling runs in parallel. Nuts are cleaned and graded so the size band matches the cavity. Roasting drives moisture down and develops aroma while keeping the nut crisp. Cooling follows immediately, so residual heat does not soften caramel or melt cream fats later. Skin removal reduces bitter flecks and improves adhesion in the cream stage. Whole nuts are then singulated so they can be placed one by one. The hazelnut cocoa cream is prepared as a fat, continuous paste. Roasted hazelnuts are milled into a smooth nut paste with controlled temperature so oil does not separate. Sugar and cocoa solids and dairy solids are blended into this paste. Refining reduces particle size so the cream feels smooth rather than gritty. The cream is then mixed under controlled heat so viscosity becomes consistent and air is minimized. Emulsifiers can be introduced to tune flow and prevent oil bleed. The finished cream is held warm enough to pump but cool enough to keep flavor stable. Chocolate for the cap is produced and tempered to a stable crystal form. Chocolate is melted and filtered so no unmelted fragments remain. It is then tempered in a continuous tempering unit that heats and cools in stages. The goal is a chocolate that flows well but sets fast with gloss and clean release. Viscosity is monitored because cap thickness depends on flow through small nozzles. Assembly begins on a tray or belt line that carries a field of cavities. The cavities act as the master geometry for the product. Each cavity receives each component in sequence with tight timing. The first operation deposits caramel into each cavity as a measured shot. The shot is designed to form a cup rather than a flat puddle. This is done by using nozzle geometry and deposit motion that pushes caramel up the cavity walls. Immediately after deposit, a forming tool can shape the caramel cup. A punch or dome tool presses into the caramel to create a bowl profile. Tool temperature is controlled so caramel does not smear or stick. Dwell time is short, so the line speed remains high. The tool retracts and leaves a consistent hollow with a defined rim thickness. Caramel cup geometry is a major control point. Wall thickness must be thick enough to hold during nut insertion. Wall thickness must not be so thick that the bite becomes overly chewy. Rim geometry must be clean because the rim later interfaces with cream and the chocolate cap. If the rim is uneven, the cap can sit crooked and leave gaps. After cup forming, the cavities pass through a short cooling section. This cools the caramel surface to increase strength for nut insertion. Cooling is tuned to firm only the surface layer while keeping the bulk plastic. A fully hardened caramel would crack when a nut is pressed in. A too soft caramel would allow the nut to sink and deform the cup. Nut insertion follows. Nuts are fed from a singulator that orients each nut. A placement head drops or presses one nut into each caramel cup. Placement force is controlled so the nut seats at a consistent depth. The nut must be centered so the final piece balances. Off-center nuts can create thin caramel walls that tear. The nut is pressed enough to anchor without breaking the nut. Next, the nut cream is deposited around the nut. The depositor nozzle enters the cavity and dispenses a controlled volume. The cream must flow around the nut and fill the annular space. It must also avoid trapping air under the nut or along the cup wall. To control air, the deposit can be staged as a first ring and then a top fill. The nozzle motion can trace a small circle to wet the wall evenly. Cream viscosity is tuned for this step. If the cream is too thin, it floods and can overflow the rim. If it is too thick, it bridges and leaves voids. Void formation is a defect because it weakens structure and creates visual gaps under the cap. The line controls cream temperature tightly because temperature is the fastest way to shift viscosity without changing formulation. After cream deposit, the surface is leveled. A small leveling blade or vibration can flatten the cream surface. Leveling ensures the chocolate cap will sit evenly. It also ensures the cap seals the cavity edge without a high spot that would break later. Leveling is gentle because excessive vibration can move the nut and distort the cream ring. Chocolate capping follows immediately after leveling. Tempered chocolate is deposited as a disc onto the cavity opening. The disc must bond to the cream and rim and then set without cracking. Deposit weight defines cap thickness, which controls snap and protects the interior. If the cap is too thin, it can fracture during tray packing. If too thick, it can dominate the bite and slow setting. To achieve a clean cap, the chocolate is deposited at a temperature where it spreads slightly, then stops. The mold geometry helps define the cap edge. Some lines use a light vibration after capping to remove bubbles and ensure contact. Vibration must be limited because it can cause chocolate to run down the cavity walls and change appearance. M&Ms are produced by forming uniform chocolate-based centers, then building a hard sugar shell through controlled panning cycles, then applying color and a final gloss coat before high-speed packaging. Center manufacture starts with chocolate preparation because the center defines final size and how the shell grows. Chocolate ingredients are blended into a fat continuous mass where sugar and milk solids are dispersed. The mass is refined to reduce particle size and eliminate grit. Conching follows to redistribute fat and reduce moisture while smoothing flavor. Tempering then sets the cocoa butter crystal form so the centers solidify quickly and remain stable during shell building. Centers can be plain chocolate or can include inclusions depending on format. For plain centers, the tempered chocolate is deposited into molds or onto a cooled belt. Molded centers use multi-cavity molds shaped as small domes. Depositing systems meter a precise mass into each cavity, and vibration removes trapped air. Cooling tunnels then solidify the chocolate until it releases cleanly from the mold. Belt-deposited centers are dropped as small buttons and then shaped by controlled vibration or light rolling to create a consistent pellet. When inclusions are used, they are incorporated during depositing. Nuts or crisp pieces are pre-sized and coated lightly so they do not shed fines. Inclusion dosing must be consistent because it changes mass and shape. The chocolate must wet the inclusion surface and then set without voids. Void-free centers roll more predictably in panning and resist cracking. After forming, the centers are conditioned. Conditioning brings temperature into a narrow band where the chocolate is firm but not brittle. If centers are too warm, they deform under tumbling loads. If too cold, they chip at edges and create sharp points that can pierce the shell. Conditioning also stabilizes surface moisture, so the first sugar layers bond consistently. Shell building uses rotating pans or perforated coating drums. Centers are loaded to a defined bed depth. Drum speed is set, so the pieces roll continuously and do not slide. Rolling is essential because the shell grows by repeated thin layers that must distribute evenly around each piece. The first shell layers act as a sealing and adhesion stage. A thin syrup is sprayed onto the rolling bed. The syrup wets the chocolate surface and forms a sticky film. Dry air then removes water, so the film crystallizes and locks on. This stage must be gentle because too much liquid can dissolve the surface or cause pieces to stick. Small additions, followed by full drying, create a stable base for thicker layers. After adhesion is established, the process shifts to bulk shell growth. A higher solid sugar syrup is sprayed in pulses. Immediately after spraying, a fine sugar powder can be dusted over the bed. Powder absorbs surface moisture and accelerates setting. Drying air then drives water out and promotes crystal growth through the layer. This spray dust dry cycle repeats many times. Each cycle adds only a small mass, so stresses do not accumulate. Drying control is critical because sugar crystallization defines hardness and surface quality. If drying is too rapid, the surface can harden while internal moisture remains. Trapped moisture later creates pitting or weak shells. If drying is too slow, the surface stays tacky and pieces can twin. Twin pieces stick and create double shapes that cannot be sold. Air temperature and humidity and airflow rate are tuned so each layer sets fully before the next spray. As the shell thickens, the process adjusts. Mechanical intensity. Early on, the bed motion is gentle to avoid deforming centers. Later, the shell is strong enough for slightly higher speed, which improves rounding. Excess speed creates chips, so adjustments remain small. The objective is a near spherical shape for standard M&Ms. Shape uniformity helps printing and improves flow in packaging. Shell thickness is monitored by mass gain and by size checks. The line targets a final shell to center ratio that controls crunch and dissolution time. Too thin a shell yields soft bite and color rub. Too thick a shell yields excessive crunch and longer dissolve. Thickness control is achieved by counting cycles and controlling syrup solids and spray rate. When the shell is near final thickness, the process transitions to smoothing layers. Smoothing uses lower spray volumes and less powder. Thin syrup films flow into micro roughness created during bulk build. Longer drying times then lock a smoother surface. Smoothness matters because it improves gloss and makes the final printed mark sharp. Color application is done as a sequence of thin coats. Color solutions are prepared at controlled concentration and filtered. Color is applied by spraying a tinted syrup or a color solution onto the rolling bed. Drying follows after every pass. Multiple light passes build saturation without streaking. Heavy application would pool in low spots and create blotches. Different colors are normally processed in separate runs to prevent cross tint. Changeover includes flushing spray lines and cleaning pan surfaces. Shade control is performed by optical measurement. Adjustments can be made by changing concentration or by adding additional light passes. The final shade must be stable under polishing and handling. After color is established, the shell receives a protective clear finish. A clear syrup or glaze coat can be applied in thin layers. This coat smooths the surface and reduces pigment rub off. It also creates a base for polishing. Drying after clear coats is extended to drive moisture to a stable endpoint. Moisture endpoint matters because residual moisture can cause stickiness and dull gloss. Polishing is performed after the shells have equilibrated. Pieces move into a polishing pan with gentler tumbling. A polishing agent is applied as a fine mist. The pieces roll and the film spreads and fills micropores. This creates the characteristic shine and reduces friction. Reduced friction improves flow through hoppers and reduces scuffing. Polishing must be controlled because too much polish can feel waxy and can interfere with printing. For marked M&Ms, the letter is printed near the end of finishing. Printing uses edible ink transferred by a pad printing system. The candies are fed into a positioning system that presents a stable face. The pad picks up ink from an etched plate and transfers it to the candy surface. Ink viscosity and pad pressure are tuned so the mark is crisp. The surface must be dry and smooth for good adhesion. After printing the pieces, pass through a short drying stage so the ink sets. Conditioning after printing stabilizes the finished shell. This stage allows moisture and temperature to equalize and reduces internal stress. Stable conditioning improves resistance to cracking during packaging. It also ensures the polish and ink films are fully set. Sorting and screening remove defects before packaging. Vibratory screens remove fines and broken pieces. Optical sorting can remove twins and off-color pieces and pieces with missing print. Size grading ensures consistent diameter. These steps improve appearance and also protect packaging machines from jams. Conveying to packaging is designed to minimize impacts. Drop heights are kept low and chutes are smooth. Hoppers are designed to prevent bridging. Feeding systems deliver a steady flow to weighers. Excess vibration is avoided because it can chip shells and generate dust. Portioning uses multi-head. Weighers for bag formats. The candies are distributed into many small hoppers. Software selects combinations that meet target weight. The portion drops through a funnel into a bagging machine. Bagging uses vertical form fill seal systems, where film becomes a tube and seals are made above and below the drop. Seal timing keeps candies out of the seal area. Barrier films protect against moisture, which would soften shells and dull gloss. For tube formats, the process may use counting or volumetric dosing. A counting system uses sensors to count pieces as they fall into tubes. Volumetric systems use cups that measure a defined volume. Tubes are capped and then labeled. For carton formats, the candies are dosed into cartons, and the cartons are closed and glued. Each format relies on consistent flow and low dust. Case packing groups finished units into shipping cases. Cases are sealed and coated. Palletizing stacks cases to reduce movement. Storage conditions are held stable to protect. Chocolate and shell. Temperature swings can cause chocolate expansion and contraction, which stresses the shell. Stable conditions reduce cracking and help maintain gloss. Astros are manufactured by forming small chocolate-based centers with tight size control, then building a hard sugar shell in rotating pans, then applying color and a final gloss so the pieces pour cleanly and resist scuffing. Center production starts by creating a stable chocolate mass with the right flow and snap. Cocoa solids, sugar, and milk solids are combined with cocoa butter and mixed until the powders are fully wetted. The mixture is refined to reduce particle size, so the center feels smooth rather than gritty. Conching follows, where heat and shear drive off residual moisture and redistribute fat, so viscosity becomes predictable. The chocolate is then tempered, so cocoa butter crystallizes in a stable form that sets fast and resists bloom. This temper step matters because centers must survive long tumbling. Cycles without softening or smearing. Center shaping is designed around uniform mass and consistent curvature. Tempered chocolate is deposited in precise portions, either into shallow dome molds or onto a cooled steel belt. Mold depositing uses metered pistons that deliver the same dose every time. Vibration removes trapped air and levels the surface so each center has the same profile. Belt depositing forms small buttons that are shaped by controlled vibration or light rolling. Both approaches aim for the same lens, like pellet that will roll evenly in a coating pan. When inclusions are used, the inclusion stream is stabilized before it touches chocolate. Crisp pieces or nut fragments are screened to a narrow size band. Fines are removed because they make dust and create weak spots in the center. The inclusions are then metered into chocolate at a controlled ratio. The chocolate must flow around each inclusion and fill voids. Voids create weak points that later crack under shell, stress. After forming, the centers are cooled in stages. Early cooling pools heat out quickly to lock shape. Later cooling slows down to reduce internal stress. A controlled cooling profile produces centers that release cleanly and have consistent hardness. The centers then enter conditioning, where temperature is brought to a stable range for panning. Centers that are too warm deform during tumbling. Centers that are too cold chip at the rim and create sharp edges that can pierce the shell. Shell building begins in rotating coating pans or perforated drums. The pans are loaded to a defined bed depth, so the pieces roll in a continuous cascade. Rotation speed is tuned so pieces roll rather than slide. Rolling ensures every surface sees the same spray and drying exposure. Sliding creates flat spots and uneven layer thickness. The first shell layers are an adhesion stage. A light sugar syrup is atomized into a fine mist and applied in short pulses. The syrup wets the center surface and forms a thin film. Dry air follows immediately and drives off water, so the film crystallizes and locks in place. This stage must avoid excess liquid because wet centers stick together and form twins. It also must avoid slow drying because tack persists and collisions bond pieces. After adhesion, the process shifts to bulk shell growth. A higher solid syrup is sprayed onto the rolling bed. Fine sugar is often dusted on top of the wet film. The dust absorbs moisture and speed setting. Airflow then dries the layer and drives crystallization through its thickness. This spray, dust, and dry cycle is repeated many times. Each cycle adds only a small amount of mass, so the shell builds gradually without large stress jumps. Crystallization control drives shell strength and surface quality. If drying is too aggressive, the surface can harden fast while moisture remains inside the layer. That trapped moisture later escapes and forms pits or weak spots. If drying is too gentle, the surface stays. Sticky and pieces can clump. Air temperature and humidity and airflow rate are tuned, so each layer sets fully before the next spray. Syrup concentration is also controlled because higher solids set faster, but can create roughness if they crystallize too quickly. As the shell thickens, the process adjusts how it manages shape. Early on, the bed motion stays gentle because the center is still close to the surface and can be damaged. Later, the shell has enough thickness to take slightly more impact. Increased rolling helps round the pieces and smooth high points. Impact must still be limited because chips create exposed layers and color defects later. Shell thickness is managed by mass gain and by dimensional checks. The line targets a shell to center ratio that defines crunch and dissolve time. A shell that is too thin will scuff and show color rub. A shell that is too thick will feel overly hard and can crack when bitten. Thickness is tuned by the number of build cycles and by syrup. Solids and spray rate. Surface refinement starts when thickness is near target. The process reduces powder addition and uses thinner syrup films. Thin films flow into micro valleys and smooth the texture. Longer drying times then lock the smoother surface. Smoothness is important because it improves gloss and reduces abrasion in packaging. It also supports sharp color appearance because rough surfaces scatter light. Color is applied as controlled outer layers rather than as a single heavy coat. Color solutions are prepared in mixing tanks with tight concentration control. They are filtered so no undissolved particles reach spray nozzles. Color is applied in light passes and dried fully after each pass. Multiple passes build saturation without streaks. Heavy color application would pool and create blotches. Light passes allow the bed motion to distribute color evenly. Color timing matters. Applying color too early risks burying pigment under later structural layers. Applying color too late risks poor adhesion because the shell surface is already very hard. Many lines introduce color after the shell has most of its thickness and still has enough surface receptivity. Then they lock color with a few clear layers that reduce rub-off and improve durability. When multiple colors are produced, the process usually runs each color in separate batches. Separate runs reduce cross-tint and keep shade consistent. Between colors, the spray system is flushed and the pan interior is cleaned to remove residual pigment. Shade checks are performed on samples. Adjustments are made by changing pass count or concentration. The goal is a tight shade window across the entire run. After color, the shell receives a protective finish stage. Clear syrup coats can be applied in very small amounts. These coats smooth the surface further and help protect pigment. Drying after clear coats is extended to reach a stable moisture endpoint. Moisture endpoint is critical because residual moisture causes stickiness and dull gloss. Too little moisture can make shells brittle and prone to chipping. Moisture equalization follows the final drying. Even when the surface feels dry, the inner shell can hold a slightly different moisture level. Equalization holds the product in controlled air so gradients flatten. This reduces internal stress that can show up as fine cracking. It also stabilizes the surface for polishing because polish spreads best on a consistent substrate. Polishing creates the characteristic shine and improves flow. Polishing is done in a separate pan with gentler tumbling. A polishing agent is applied as a fine mist. The pieces roll and the film spreads across the surface through repeated contact. The film fills micro pores and reduces friction. Reduced friction lowers scuffing and improves how the pieces move through hoppers and chutes. Polishing must remain controlled. Too little polish leaves a matte surface that sheds sugar dust. Too much polish can feel waxy and can increase slip in handling. The process, therefore, uses small additions with extended tumbling between them. This lets the film distribute evenly and avoids wet spots that would cause clumping. Dunkin' Donuts production starts with formulation of base dough using a high-capacity spiral mixer. Ingredients are loaded automatically through overhead dispensers connected to silos and tanks. The dry phase includes high-gluten wheat flour, sugar, salt, non-fat dry milk, and dough conditioners. Liquid components include water, whole eggs, vegetable shortening, and yeast. Ingredients enter the mixing chamber in a fixed order to ensure consistency. Flour is dispensed first into the bowl, followed by sugar and salt through calibrated rotary valves. Shortening is pre-melted in a jacketed vessel and dosed into the bowl using a metered pump. Liquid eggs are held in chilled tanks and dispensed through a pneumatic valve. Yeast is hydrated in a separate tank before being introduced into the mix stream. Mixing begins at a low speed to hydrate the flour and form gluten strands. The mixer transitions to a higher speed to fully develop elasticity. Total mixing time ranges between 8 and 12 minutes depending on batch size and target temperature. Bowl temperature is monitored through probes to prevent overheating. Once dough reaches optimal extensibility and temperature, it is discharged into a dough handling conveyor. This conveyor feeds a volumetric divider equipped with servo-driven pistons that portion dough into uniform units. Each portion is shaped into a ball using a rotary rounder. Rounded dough balls are transported by a belt conveyor into a multi-level proofer cabinet. Inside the cabinet, humidity and temperature are controlled to activate yeast fermentation. The dough rests for 30 to 60 minutes based on size and environmental conditions. After proofing, dough pieces exit the cabinet and enter a forming machine configured for ring shapes. A sheeter flattens each piece to a fixed thickness. A dual-blade rotary cutter stamps the dough into rings and removes the center to create the hole. Waste dough is automatically conveyed back to the hopper for reprocessing. Cut dough shapes are placed onto paper-lined proofing trays by a pick-and-place arm. Trays are loaded onto racks that feed into a secondary proofer tunnel. This tunnel maintains consistent humidity and temperature for final rise. Final proofing continues until dough height reaches preset targets. Proofed rings are then transferred onto a mesh belt conveyor leading into the frying system. The fryer is filled with vegetable oil, maintained at 190 degrees Celsius using immersion heating elements. The belt submerges each donut halfway and flips it midway to ensure even browning. Frying time is approximately 90 seconds per side. Excess oil is removed at the fryer exit using an inclined drip section. A vibrating shaker assists in shedding residual surface oil. Donuts proceed to a cooling conveyor that circulates ambient air over the surface to reduce internal temperature before finishing. Cooled donuts are sorted into finishing lines based on type. Plain rings move to the glazing station, which includes a curtain coater that pours warm sugar glaze over moving donuts. Excess glaze is recovered by a recirculation pump. Coated donuts pass under an air knife to remove drips and ensure uniform coating. For powdered sugar varieties, donuts are diverted into a tumbling drum. Fine sugar is dispensed into the drum continuously as donuts rotate inside. The tumbling motion creates full surface coverage. Sugar fines are filtered and reused through a vibratory sifter. Chocolate-coated donuts are transferred to an enrobing line. Melted chocolate compound is maintained at 38 degrees Celsius in a reservoir and pumped to a waterfall applicator. Donuts pass under the waterfall and receive a full coating. An inline cooling tunnel solidifies the chocolate layer. Filled donuts follow a different path. These start as solid discs cut from sheeted dough and proof separately. After frying and cooling, each unit is aligned on a conveyor with a multi-nozzle injection machine. The filling system uses positive displacement pumps to inject jelly, custard, or cream into each donut at a fixed volume. Nozzles penetrate the side and retract automatically after filling. Decorated donuts are moved to a robotic icing station. Each robot arm uses a temperature-controlled piping nozzle to apply icing patterns or toppings. Sprinkles are deposited via gravity-fed hoppers positioned above a vibrating grid. Icing is cooled rapidly with a chilled air tunnel to prevent smearing. Donuts requiring packaging are grouped using a photo eye sensor and placed into trays by a robotic loader. Trays are conveyed to the overwrapping station where a film is wrapped and sealed using a heated jaw. Packaged trays proceed to a labeling machine that applies product and date information. Donuts intended for retail stores are stacked into crates by a pusher arm. Crates are conveyed to a loading dock and stored in temperature-controlled bays before transport. Crate movement is sequenced based on product age to maintain first-in, first-out flow. Throughput is maintained by synchronizing mixing, proofing, frying, glazing, filling, and packing stages. Any discrepancy between steps is corrected by buffer zones built into the conveyor system. Sensors at each handoff point check for weight, position, and spacing. Dough properties are controlled through water temperature, flour hydration, and mixer speed. Yeast activity is adjusted using proofing time and sugar content. Fry color and texture are determined by oil temperature, dwell time, and surface evaporation rate. Glaze thickness is adjusted by flow rate and curtain gap. Chocolate viscosity is controlled with continuous mixing and temperature monitoring. Filling density depends on nozzle diameter and injection pressure. Sprinkle adhesion is determined by icing tack time and coating temperature. Rework dough is monitored to prevent excessive cycles which could affect gluten structure. Oil is filtered continuously through a mesh screen and replenished to maintain performance. Icing and glaze are discarded after exceeding hold time limits. Mechanical components are cleaned using a clean-in-place system for mixers and pumps. Fryer oil is drained and replaced after a fixed number of cycles. Filling stations are purged between flavor changes using heated rinse cycles. Donut size is kept uniform through automated cutting, proofing, and handling. Each unit is weighed inline using load cells before frying. Out-of-spec pieces are rejected by air jets and sent to waste bins. Color is monitored by optical sensors after frying and coating. Each production run is tagged with a digital identifier that tracks every batch of dough from mix to packaging. Operators interface with the line through touchscreen HM. is that adjust process parameters and initiate recipe changes. The ring shape is maintained by cutter pressure, proofing time, and dough elasticity. Hollow centers expand predictably when gluten structure and gas production are balanced. Sidewalls form evenly when frying is performed at the correct temperature gradient. Filled donuts expand less during frying due to the absence of a central void. Filling volume is calibrated to prevent leakage and to ensure weight compliance. Injection heads are sanitized between runs using a self-cleaning piston flush system. Production of limited-time donuts uses custom molds or dies fitted to the standard sheeting line. These are swapped in and out using quick-release clamps mounted on the cutting head. All process conditions remain unchanged except for shape and possibly finish. The Dunkin' Donuts production process is defined by sequential control over dough preparation, shaping, frying, finishing, and packaging. No stage is manually operated after initial ingredient loading. All transfers are automated and time synchronized. Mechanical reliability is ensured through routine calibration of volumetric dividers, fryer controls, coating pumps, and injection systems. Sensors detect clogging, misalignment, or loss of temperature and alert the PLC for correction. Air quality around finishing zones is maintained using filtered ventilation that prevents icing contamination. Powder applicators are enclosed and use vacuum returns to contain sugar dust. Chocolate lines are enclosed and climate controlled to prevent blooming. Every donut passes through at least 8 separate mechanical systems before final packaging. Each system modifies dough, temperature, texture, filling, or coating in a defined and repeatable way. The outcome is a donut with precise dimensions, weight, color, and taste profile. Wendy's burgers begin with raw ground beef held in refrigerated stainless steel bins, fitted with auger-driven dispensers. The beef is pre-ground to a fixed particle size and loaded into a hopper positioned above the patty forming system. The patty forming machine uses a hydraulic ram to compress a measured quantity of beef into a square mold. The square mold consists of a cavity with sharp edges and adjustable depth to control thickness. The beef enters the mold vertically and is pressed to a target shape using downward force. A release plate ejects the formed patty onto a conveyor belt lined with a non-stick food-grade belt material. The patties travel on the belt to a pre-cooked staging zone where they are spaced using an optical sensor and gating arm. Each patty is indexed into a clamshell-style contact grill, which applies uniform pressure from above and below. The upper platen is heated with embedded electrical elements and lowered using pneumatic pistons. The bottom platen remains fixed and maintains a set temperature through thermal sensors. Cook time is controlled by belt speed and platen temperature. Average dwell time for each patty is between 100 and 120 seconds, depending on thickness and grill load. Internal patty temperature is monitored using inline thermal probes, which retract automatically after contact. Surface browning is caused by Maillard reactions accelerated by the grill temperature. Rendered fat drains through grooves in the lower platen and is collected in a drip pan. Excess steam is evacuated through a hood system positioned directly above the grill zone. Once cooked, the patty exits the grill and moves onto a staging tray held at a constant holding temperature using a heat lamp array. While patties are cooking, buns are prepared on a separate toasting line. Buns arrive from storage in trays and are unloaded onto a conveyor. The bun separation system uses rotating paddles to split top and bottom halves and align them face down on the line. Each bun half passes under a radiant toaster element, which operates at a fixed distance above the surface. Toasting time is determined by conveyor speed and element intensity. Bottom buns are toasted slightly longer than top buns to handle moisture from toppings. After toasting, buns proceed to the assembly belt where they meet other components. Burger toppings are prepared on parallel preparation lines. Leaf lettuce is pre-cut and washed, then stored in chilled bins and dispensed manually into bins along the line. Tomatoes are sliced using a rotary blade slicer that maintains uniform thickness. Slices are collected into trays and moved to the topping line by belt conveyor. Onions are peeled and cut using an automated ring slicer and loaded into shallow pans. Pickles are pre-sliced and held in brine-filled containers until use. Cheese slices are separated by a vacuum picker and fanned out onto a chilled tray. Condiments, including mayonnaise, ketchup, and mustard, are dispensed using trigger-activated pumps that release a fixed volume per stroke. Dispensers are calibrated to deposit evenly without spread beyond the bun area. Burger assembly begins with bottom buns moving along a belt aligned with the topping line. A pump dispenses mayonnaise directly onto the bun in a circular pattern. A square cooked patty is placed onto the bun using a precision-guided placing arm, or manually depending on station configuration. Cheese slices are placed directly on top of the hot patty, which softens the cheese slightly but does not fully melt it. Sliced tomato is added next by tongs or fingers placed at center alignment. A leaf of lettuce is layered over the tomato and adjusted to not overhang the bun. Onion rings are laid flat across the lettuce with no stacking. 2 or 3 pickle slices are placed side by side depending on diameter. Ketchup and mustard are dispensed in zigzag or dot patterns based on the specific burger recipe. The top bun is retrieved from its place on the parallel conveyor and inverted onto the built stack using a rotating arm. The complete burger is then moved forward to a wrapping station where it is enveloped in printed foil or wax paper. Wrapping is done by folding each side toward the center and then folding the base upward before rolling the package forward. Wrapped burgers are placed into holding bins arranged by product type. Bin trays are heated from beneath with radiant elements to hold temperature. Burger names and identifiers are shown on digital displays above each bin. The wrapped burgers are then pulled in the order of assembly requests from service or drive-through lines. For specialty burgers with additional ingredients, separate modules are added to the line. Bacon is pre-cooked in convection ovens and held on heated trays. Spicy toppings or sauces are dispensed through separate triggers. Extra patties are added by adjusting tray positions to align multiple cooked patties before final topping. The entire burger line is modular and designed for high throughput. Each step, from toasting to wrapping, is timed and paced using conveyor intervals and operator rhythm. Cooked patties are used within a fixed window to maintain thermal properties during assembly. The square patty shape aligns precisely with the round bun through placement guides. Cheese coverage is optimized by placing the slice diagonally across the square patty. Lettuce folds are standardized to reduce overhang and dripping. Tomato slices are inspected visually for diameter and replaced if undersized. Onions are separated into ring layers to maintain consistent thickness. Pickles are spaced to prevent overlap or bunching. Sauce volumes are adjusted using pump restrictors. Each pump cycle delivers a metered dose that is verified weekly by weight checks. Dispense angles ensure center placement with minimal deviation. Top bun pressure is measured periodically to confirm compression does not exceed tolerance. Overcompression can cause lettuce or tomato slippage. Wrap tightness is checked by torsion testing with digital force gauges. Grill platen pressure is balanced to avoid sear marks that penetrate too deeply. Contact time is calibrated to match patty water content and surface heat conductivity. Belt tension is maintained through spring-loaded rollers at both ends of the grill. Drip pan contents are filtered and cooled before disposal. Grease flow is measured to calculate fat loss per batch. Each tray of patties is weighed at intervals to confirm moisture retention and yield. Conveyor speed is set to match maximum output per cook zone. Bun toast time is synchronized to meet grill exit timing. Topping replenishment occurs based on tray weight thresholds detected by load cells. Tomato and onion prep stations are cleaned and reset every few cycles to prevent buildup. Cheese trays are kept below 5 degrees Celsius using chilled gel plates. Lettuce bins are sloped for continuous access without compaction. Burger stacking alignment is controlled by operator training and guided bins. Variants like double burgers use the same assembly line with secondary patty placement after cheese. Burgers with spicy or grilled ingredients use segregated stations to prevent flavor transfer. All process parameters are displayed on line-side screens for real-time monitoring. Operators adjust pump pressure, toast speed, and tray positions based on on-screen instructions. Each station is time-stamped to maintain consistency across shifts. Ingredient freshness is managed by rotation schedules and bin timers. No topping remains in use beyond its designated holding time. Each component has a separate preparation and service life which governs when trays are replaced. The square patty ensures uniform cooking and reduces edge shrinkage. Griddle contact area is maximized by flat pressing. Consistent doneness is achieved across all patties through center-out thermal profiles. The full Wendy's burger is formed by layering precise ingredient units in defined order. Each addition is made at a fixed position along the conveyor. The sequence ensures balance in flavor, weight, and thermal distribution. Assembly line pacing is regulated by burger type, quantity, and order load. Stack height is limited by bun compression threshold. Burgers are finalized within a tight time window to maintain optimal serving temperature. Pizza Hut. Pizza production begins with the preparation of pizza dough using automated high-capacity mixers. Each batch starts with high-protein wheat flour dispensed from overhead silos through a pneumatic conveyor into a stainless steel mixing bowl. Water is metered precisely from a temperature-controlled supply line and delivered into the bowl through solenoid valves. Instant dry yeast is stored in sealed bins and dispensed by auger into the bowl after water. Salt and sugar are pre-weighed and released into the bowl from vibratory feeders mounted above the mixer. Vegetable oil is pumped from a storage tank through a heated line and added last to ensure uniform distribution. The spiral mixer begins in a slow speed mode for 1 minute to hydrate the dry ingredients. After hydration is complete, the mixer shifts to high speed to develop gluten structure. Mixing continues for 8 to 10 minutes until the dough reaches a defined elasticity and target temperature range. The dough is discharged into a trough and transferred to the divider using a hydraulic lift arm. The divider uses a piston system to cut dough into fixed weight portions based on pizza size specifications. Each dough piece is rounded into a ball shape by a rotary rounding mechanism and deposited onto a lightly floured tray. Rounded dough balls are conveyed into a temperature and humidity-controlled proofing cabinet. The proofing stage allows yeast fermentation to produce gas and relax the dough structure. Temperature is held around 38 degrees Celsius and humidity near 85% to maintain surface softness. After proofing for approximately 1 hour, the dough is moved to a pressing station. Each ball is loaded onto a heated platen, which presses the dough into a disc shape. Pressing is done with a hydraulic top plate that flattens the dough to a specified diameter and thickness. Heat from the platen sets the shape and prevents shrinkage during later handling. Pressed dough discs are transferred to perforated baking pans or screens using a vacuum lifter. A light mist of oil is applied to the pan surface to prevent sticking. The dough and pan then move along a conveyor to the topping line. Topping application begins with sauce deposition using a volumetric piston filler. The sauce is pumped from a heated holding tank and dispensed in a spiral pattern starting from the center of the dough. A rotating disc beneath the pizza ensures even coverage without manual spreading. Shredded mozzarella cheese is stored in chilled hoppers and fed to a depositor via a vibratory conveyor. Cheese is distributed through rotating paddles that drop a measured weight evenly across the surface. Cheese coverage is calibrated to stay inside the dough border. Additional toppings are added in a fixed sequence depending on pizza type. Pepperoni slices are dispensed from a rotary carousel that places overlapping slices in concentric rings. Cooked sausage crumbles are metered through a hopper with a gate-controlled release. Vegetable toppings such as mushrooms, green peppers, and onions are added from separate hoppers using calibrated volumetric scoops. Bacon pieces and ham strips are dispensed from compartments, lined with agitators to prevent bridging. Olives are dropped from a chute fitted with a shaker plate to ensure even distribution. Pineapple chunks are added last and drained before dispensing to avoid excess moisture. Each pizza proceeds to the oven loading belt, which is synchronized with baking time and oven speed. The pizzas enter a conveyor oven with a stone or mesh belt and a controlled baking chamber. Top and bottom heat are separately adjustable using electric elements or gas burners. Baking time is generally between 6 and 7 minutes, depending on pizza size and topping load. The oven is divided into thermal zones which apply different temperatures to optimize crust and topping finish. Air circulation fans maintain uniform heat distribution within the chamber. Crust browning is controlled by bottom belt temperature and pan contact. Cheese melt is regulated by top zone intensity. Sauce bubbling and topping cooking are completed within the dwell time set by conveyor speed. Once baking is complete, the pizza exits the oven and is transferred onto a staging table with a heat-resistant surface. A metal lifter is used to remove the pizza from the baking pan if one was used. The pizza is then slid onto a cutting board positioned below a rocker blade cutter. The cutter is hinged to apply uniform downward pressure and is guided by slots in the board to maintain equal slice sizes. Standard cut configurations are 4, 6, or 8 slices depending on diameter. Each pizza is rotated to complete perpendicular cuts if required. Cut pizzas are transferred onto corrugated cardboard discs which serve as a support base. The pizza and disc are inserted into printed boxes by a sliding motion, which prevents topping displacement. Boxes are closed with a fold lock mechanism and stacked in batches on a heated shelf for holding. Specialty pizzas with cheese-stuffed crust use a different pressing process where cheese sticks are inserted into the dough edge before sealing. The dough is crimped mechanically to enclose the cheese along the perimeter. These variants are baked with slightly longer dwell times to ensure cheese softening. Thin crust pizzas skip the proofing stage and are sheeted directly after mixing. The sheeting line flattens dough using a 3-stage roller system that progressively reduces thickness. Sheeted dough is cut to shape using a rotating die and docked to prevent bubbling. It is transferred directly to the topping line without additional rise. Pan pizzas use thicker dough portions which are hand-pressed or machine-pressed into deep pans coated with oil. The oil creates a fried base texture during baking. These pans are baked longer at lower temperatures to prevent surface burning. Pizza Hut production lines are modular and can run multiple styles concurrently by using different lanes. Each lane is fed by a shared dough room and topping prep area. Toppings are staged in mobile chilled carts that are swapped based on menu rotation. Sauce preparation occurs in a separate area where tomato concentrate is blended with water and seasoning. The sauce is cooked in steam kettles and cooled rapidly before being pumped to holding tanks. Cheese is shredded in-house using rotary drum shredders or received pre-shredded in lined totes. Toppings are prepared using a combination of manual and automated methods. Whole vegetables are washed and sliced on rotating blade machines. Meats are pre-cooked and diced using high-speed dicers or crumblers. Toppings are loaded into color-coded bins and inserted into the topping line feed hoppers. Ingredient flow is monitored by load cells under each hopper, which signal refill triggers when weight drops below threshold. Each depositor is linked to a PLC that controls dispense rate, duration, and alignment. Pan and tray washing systems clean and sanitize bakeware after each use. Washed pans return to the pressing line in timed cycles. Conveyor belts are brushed and wiped at shift intervals to remove topping residue. All components of the pizza undergo mass balance verification to ensure recipe compliance.